Hey, welcome back, man. One of the greatest parts of doing the show, it is truly a gift that I get to pick my own guests. And next to evolutionary psychology, the thing that I've been most obsessed with for the last 2 decades is astronomy, astrophysics, quantum mechanics, relativity, all that stuff, Newtonian physics. And my guest today is a buddy of mine that I've met from going to the UNLV School of Physics, where I went to monthly seminars, and he is a guy that I met, and he's got his PhD from Montreal, Canada. He has a master's in science from the University of Toronto. He has a PhD in theoretical physics from Cornell University, and this is Mr. Sergei Dyda. Is that correct?
That's correct.
Dr. Sergei Dyda, so glad to have you. You were also at, where you were a professor at UNLV. Were you a professor, or were you a researcher?
I was a humble researcher.
Researcher at UNLV, and then you were at Cambridge.
At Cambridge, and now at University of Virginia.
And now you're a Virginia, what did we say before?
Cavalier.
Cavalier. You're Virginia Cavalier. That's off. So you're a full professor there? You're still you're a research associate?
Still a research associate.
Okay. All right. That's awesome. But I actually have a theoretical physicist on here. Thank you, Mom. I did it. All right. So I'm really glad to have Sergei on here because we have a lot of stuff to talk about. He and I have gone back and forth about a bunch of stuff. Now, your PhD, I always want to ask you about your thesis. I was trying to understand, it is magnetohydrodynamics of a protostar. Is that correct?
Of a protostar, that's right.
So, of a protostar.
So basically everything in space is a plasma.
Okay.
So unlike...
You got to go real slow. Plasma, a state of matter where all of the electrons are burned off and you're just left with hyper...
So in an atom, there's electrons and protons, and usually the electrons are orbiting around the protons.
Yeah.
So in a plasma, they're just separate.
Yeah.
They've been ripped apart.
Yeah.
And so in a plasma, you can sustain a magnetic field.
Yeah.
And so basically in space, you have all this plasma, and you have magnetic fields floating around, and they can have all sorts of physical effects.
Yeah. Okay, so just like the sun, a lot of the sun is plasma because a lot of the electrons have been burned off, and that's the state of matter that the sun would be in.
So let's use the sun as an example. So with the sun, you can get these like solar flares.
Yeah.
Right, which are like magnetic fields they're like launching particles.
Cross like this, right? Because the sun, the convection, the around the equator of the sun is rotating at a different speed than the poles. Is that correct?
And so that's going to grow this magnetic field, and these magnetic fields can then launch matter, so launch particles. And so what's happening in the sun, that solar wind, right, is relatively weak. Okay, so it's not going to go and destroy our satellites,
right?
Except when you get like a very large flare,
like what happened in was it Canada or in New York? No,
you're talking about like the Carrington event, maybe in like the 1800s.
Yeah,
like we basically just developed like electronics, and basically they all got fried from this solar flare. So basically all the what do you call it? Sending things with like Morse code, telegraph. Like all the telegraphs got fried.
Yeah, anything with an electrical component to it.
Yeah, because there was this like huge solar flare, and so this like space weather is still a huge concern now because with satellites they could all get fried if you have a similar kind of event. But to go back to like the young stars, right? That I was studying.
So protostar meaning young star.
Protostar meaning young star. So when you have like a young solar system, so imagine like our solar system,
which
like you're talking like billions of years ago.
Our solar system was originally a cloud of dust that coagulated.
Yeah, so basically what happens is you have like imagine a big cloud of like gas and dust, and it collapses on itself. And at the center, you're going to start having like a young star. So fusion hasn't yet started because the mass isn't big enough. But you still have like this core, and you still have a bunch of gas and dust that's orbiting around.
Yeah.
So imagine like a record player. Okay, so at the center of the record player is this young star, and around the record itself is this thin layer of like gas and dust. And in that kind of system, some of the gas and dust is going to fall onto the star, and the star is going to grow, and then it's going to be like a full-fledged star.
So Jupiter would be like a failed protostar. Or around the same size. At one point, Sol was probably that size. This is what I've heard before. It just didn't have enough mass in order to conduct enough nuclear fusion to become a star.
That is the current theory.
Yeah.
But forget about like a binary system.
Yeah.
There's 2 stars. Just imagine like a single star forming.
Okay.
Okay. And then in that accretion disk, so in that thin like record of gas and dust, you're going to form planets.
Okay.
Okay. And so you basically have like 10 million years. Okay, to form a planet. Because within those 10 million years, all the dust that can be used as planetary material is going to fall onto the star.
Onto the star, so you can't use it for Earth or Jupiter or whatever.
You basically have like 10 million years to grow from like little dust-sized particles that have to like clump together and then collapse via gravity, okay, to form individual planets. And so basically we're studying this kind of like young system. So what is the star part doing? I wasn't so interested in the planet formation, but I was more interested in what the star does.
The angular momentum of that dust cloud is conserved in the star. That's why all of our planets, except for Uranus, is rotating in the same direction that probably that dust cloud was also rotating it.
Yeah, that's right. So when the planets form, the gas and dust is all orbiting the same direction.
Yeah.
And so if the planets form, they're gonna still be rotating in the same direction.
And the accretion disk would be on the equivalent plane of the ecliptic now.
That's correct.
Yeah,
that's correct. And so I'm
sorry, the ecliptic is the line between the sun and the Earth, or the line that goes between whatever planet and the Earth that almost all the planets are on, except for is it Uranus that's off the ecliptic by like a pretty big distance?
I think maybe it's Pluto.
Pluto, yeah, it's one of them that's way off. Okay.
Yeah. But the basic idea is you have that like very short time frame that you need to be able to grow these planets. And so that's an important problem in current astrophysics called the meter problem.
Okay.
Because you have this dust that if you say you just have dust in the room, it can like clump with other dust.
Yes.
Via like electrostatic processes. So dust clumps together. And if you have like a big like a boulder sized thing like 100 meters across, that thing's going to start attracting things gravitationally. But how do you go from like these like dust bunnies up to like 100-meter sized rocks?
Right.
Like how do you bridge those like 6 or 7 orders of magnitude? That's a fundamental problem in planetary formation.
That does seem interesting because you end up with things like Phobos and Deimos, which are small, like 12-kilometer wide rocks.
But they can still attract things gravitationally.
Right.
Really, like, how do you go from like something that's a sand grain?
Yeah.
Because like sand grains aren't attracting other sand grains gravitationally.
Where does it start? Where does the coagulation begin?
Exactly. How do these particles coagulate? Because so you might ask, like, why do you have this 10 million year time limit? And it's because the dust particles, they don't feel pressure. Okay, and so you have gas mixed up with dust, and so the dust doesn't feel pressure. And so it basically feels a headwind from the gas. And so that headwind acts as like friction, or like you were saying, you start losing angular momentum.
Yeah.
And so that dust starts falling into the star.
Okay.
And so the rough estimate is based on how strong the headwind is, you have about 10 million years. And otherwise, you're just going to accrete everything.
So the beginning of our solar system, there's probably somewhere in maybe 30 planets, and they are getting pushed in and out mainly because of Jupiter and Saturn.
So people do these simulations where they call it an n-body simulation.
Yeah.
So you say, okay, let's put like 1 million of these particles orbiting around, and they're going to collide and kick each other, and some of them are going to clump together. Some are actually going to get ejected from the system. And then you just see, okay, where do they end up?
Yeah.
Right? And that can kind of give us clues about like how the solar system formed. Basically, there might be like patterns between like, oh, what's the distance between the first planet and the star, and what's the distance between the second planet and the star?
Right.
Because there's these things called resonances.
Yeah.
Which like, I mean, a famous example of a resonance was that bridge that just collapsed.
Yeah.
So they built, you could like look this up on Google. There's basically this bridge that they built it so that when the wind was blowing at like a certain rate, the whole bridge was just vibrating in resonance, and it ends up like just shaking like huge amplitudes.
Oh wow!
So this like a common feature in physics, where if you have a resonance, then you'll get kind of like new kinds of physical effects.
Okay.
So a resonance in planetary physics means when bodies are certain ratios away from other planets, then they're going to be like incredibly stable. So this kind of theory you can use to explain like the positions of like moons, say like Jupiter. So you look at like, oh, what's the distance between?
So Io, Callisto, Europa, and Ganymede. I believe Io is the furthest one out. Like one of them is significantly further out than the rest of them, I believe.
I think Io is the closest.
Io is the closest.
It's the one that has the really strong magnetic field.
Okay.
Yeah, and which one's the furthest?
Europa is made of almost completely of ice. Ganymede is the one that's actually larger than Mercury. Is it Callisto?
Yeah, Ganymede's the big one. I'm not sure.
Jupiter is so big that its largest moon is larger than the smallest planet. In area, not in mass. Mercury is actually larger in mass than Ganymede. here. But yeah, I think that part is pretty cool. But like you were saying that they're in resonance with each other, those four moons.
I think 3 of them are in resonance.
Because I heard that with Saturn and Jupiter that there was some kind of resonance between them.
There's all kinds of resonances between all the planets. You can at one point this theory was actually debunked, but they plotted the distance between like all the different planets and the sun, and there was some kind of like pattern that it goes like all like the squares of like certain whole numbers, and people thought there was something to it. It ended up being like incorrect. I forgot what it's called.
These are just kind of the random stable orbits that made it, right? Because the other ones didn't. They got flung out. There's probably there's a reality where Earth gets flung into Jupiter and it doesn't come out, right? There's a reality where apparently the creation of the moon theoretically as an object the size of Mars collides with the Earth's, like it kind of wings the Earth's surface and creates a splash effect that creates the moon.
That is one of the theories.
Yeah.
Actually, one of my collaborators, that was his entire thesis, was he was studying how does the moon form.
Yeah.
I'll send you the link, actually.
I would love to see that. Yeah. And because because we did carbon-based testing on the moon, we were able to tell that it came from the Earth. The moon is not something that was captured after the Earth was formed. It actually was a part of the Earth.
Yeah, those isotope studies are wild.
Yeah.
Basically, so there's different isotopes for different chemical species, and you can kind of think of it as like a fingerprint of where that like material came from.
Yeah.
And so you can actually start to use this to understand like these asteroids or like comets, like did they come from our nick of the galaxy, or are they from outside?
What's the one? Have you ever watched The Expanse?
No, I haven't.
Oh, I highly recommend it.
My old boss recommended it.
Yeah, it's my favorite TV show. And it's basically just imagine Star Trek, but they get all the physics correct. Like the ships have to fly at 1G up, and then they turn around and then they decelerate in order to land. Like they try to get all the physics correct. And I forgot it was one of Neptune's moons was captured because it's going in the opposite direction. They use that to say that came from some alien civilization that was trying to send it to Earth or whatever. It's a really cool story. But they try to keep they actually have physicists work on the show to try to keep the physics correct. But I think that part's pretty awesome. So let's get into a couple things. I do want to understand, because we started talking about protostars before. Magnetohydrodynamics is what? And by the way, get on top of the microphone here so I can.
Okay. Yeah. So magnetohydrodynamics just means you're studying how does the magnetic field that lives in this plasma.
Yeah.
How does it interact with the gas?
Okay.
So the gas we treat as a fluid. So you're doing like fluid dynamics. Okay. So a fluid is just a fancy way of saying that the individual constituents of the material, are small relative to like the separation,
the distance between them.
The distance between them. So like, say you want to study like a crowd of people, right? So like you could treat that crowd of people as a fluid, right? They're like protesting down the street. They go down like north, and then they swerve east. Like you don't actually have to follow individual people. You can just follow that. Oh, this block has like 1,000 people per block, and like way over there you have like 100 people per block. You can just treat the thing like a fluid. Yeah. And so basically everything we do in astrophysics, we just treat things like fluids. Right. And so the magneto just means that there's also a magnetic field changing how that fluid interacts.
Okay, so let's talk about this a little bit. How the gap. So I guess my first question is, let's just relate this to Mars, because I know that there's a question about the magnetosphere of Mars and how the atmosphere bled off. Would this have something to do with what you're talking about? How it wasn't able to maintain an atmosphere because it did not have a magnetic field?
Yeah. So that would be an example of a magnetohydrodynamic simulation you could do. So you can imagine you have like a star, and you blast a bunch of like magnetic flux towards this planet. Yeah. And around the planet, you put some gas that's holding it in an atmosphere, and then you might protect it with a magnetic field or not protect it.
So can you explain that to me? How does a magnetic field keep this nitrogen atmosphere on planet Earth? Like, how does that work? Is it just the gravity of Earth?
Just think of it as like, because the solar wind, there's going to be some magnetic flux that's carried with it.
Okay.
And so you're basically preventing that flux from stripping off the gas.
Okay. Now I understand what you're saying. You're saying the magnetic wind is what has blown the atmosphere off of
but
Mars.
You want another magnetic field to protect.
And there is a magnetic field on, say, Venus, which has their atmosphere. Venus's atmosphere is 90 times thicker than the Earth's. That's there because there is. Does Venus have a magnetosphere that protects it?
That's a good question. I'm not sure.
I know Venus does not have tectonic plates like the Earth does, but it's about 98% the Earth's mass. But yeah, I know Venus's atmosphere is it's 900 degrees Fahrenheit, and it's 90 times thicker than the Earth's atmosphere.
So it's really hot because the pressure is really hot.
Yeah.
But yeah, I'm not sure if there's a magnetosphere or not.
Yeah.
You have to look that up.
Yeah, for sure. And a magnetosphere is caused again because of convection inside the Earth's core. The Earth's core does not rotate at the exact same speed as the Earth's crust.
So I think it's not fully understood like what generates the magnetosphere.
Yeah.
Because if I just give you some generic planet and I ask you like, oh, why does this one have a magnetic field? Does that one not? Like people will wave their hands and say like, oh, it has something to do with what's happening in the core.
Yeah.
But I don't think anyone really
right.
understands
They're
that.
not sure because Mars would not, because it is smaller, would probably be less molten inside. I mean, there's less volcanic activity on the surface of Mars than I think on Earth. And from what I've seen with the moon doesn't have like a mantle, like a liquid flowing mantle like the Earth does.
The moon does not have like plate tectonics.
Yeah. So it does not have a magnetosphere around the moon, or it has a very weak one.
As far as I know, there's no magnetic field for the moon. Yeah.
How far does the magnetosphere of the Earth extend out? Does it extend to the moon or not that far?
I mean, in principle, it's just going to have some like drop off, like it drops off like 1 over the distance squared or whatever.
Because my understanding is the one that Jupiter has is massive and it goes out exceptionally far.
Well, so it drops off at some like rate.
Yeah.
Like 1 over distance squared, for example. So if you have a stronger magnetic field, at a certain radius, obviously if you go 10 times that distance, it'll still be stronger than some other planet that has like a weaker one.
Got it.
But yeah, Jupiter has such a strong magnetic field that it makes exploration like a problem.
Yes.
So like when we had like the Juno probe, you have to try and avoid staying in the radiation belts because you just get like slammed with particles and it just fries the electronics.
Jupiter is so massive that hydrogen acts as like a metal under the level of pressure that they have there. Is that correct?
So that's a theory about what's happening like in the core of Jupiter. So this idea that like the hydrogen in the core is going to be metallic.
Yeah.
Actually, there's a recent study where they claim that they could have metallic hydrogen at like incredibly high pressures.
Yeah.
But it hasn't. No one's actually been able to reproduce that.
Okay.
So this
interesting.
This is like a recent finding. Maybe maybe 2 or 3 years ago.
Exceptionally radioactive object that's super massive, and Jupiter is bigger than all the other planets combined.
So it's not radioactive. It's that by having you've seen the aurora borealis.
Yes.
Okay. So what causes the aurora borealis?
That's that is the lines of magnetation coming out of the Earth's poles, and then it's being irradiated, or it's having solar wind particles that are hitting.
So you have all these like particles in space that basically follow the magnetosphere lines, and then they slam into the atmosphere and make these beautiful colors.
Yeah.
So you have the same kind of effect happening with Jupiter, but because the field is stronger, you're going to get even more particles.
Yeah.
To the point that if you were just there, or your probe is there, you're going to get just slammed with a whole bunch of particles.
Got it. Makes sense.
It's going to fry all the electronics. So that's why there's going to be a new mission that's going to go to the moons of Jupiter.
Okay.
And they're choosing this kind of orbit where it's very like highly elliptical orbit.
Yeah.
So that they at some point in the elliptical orbit they're going to be as close as possible to like take good measurements.
So at the poles,
then they go back out.
Yeah.
So they get out of those radiation belts.
The pole at the poles it would be nearer to the planet, and at the equator it would be further from the planet, right?
I forgot what,
because that's why you take an elliptical. Well, maybe, I don't know. I mean, we'll see. I don't know enough about that. We're getting way into crazy stuff. The thing you wanted to talk about, or you mentioned before in the CV that you gave me, was about the formation of how black holes and what they have to do with the formation of the universe. Is that correct?
Yeah. So I think one of like the most interesting questions is what role do black holes play in structure formation?
Yes.
And in what role they play kind of like in the life cycle of the universe.
Like a supermassive black hole in the middle of a galaxy, like that type of thing?
Yeah, so imagine every galaxy has this supermassive black hole at its center. And kind of what they act as is the engine for the entire galaxy. So it's basically like a blender that recycles all the gas that's in the galaxy. So basically you'll have some gas that falls into the black hole and some that gets shot out.
Yeah.
And that gas that gets shot out, it's going to be used to generate the next generation of stars.
Okay.
And so if we want to understand like we were talking earlier about like planet formation and like what kind of like elements you have like available to make the next generation of stars and the next generation of solar systems, you have to understand what's the gas that's available. And if you want to understand that, you want to see how much of the gas was recycled by these AGNs, so by these active black holes at the center of galaxies.
Is there a limit if I continually dump mass into a black hole? Is there a limit to the point at how large the event horizon can be, or the amount of mass? Because there's a limit to a star, right? There's a point at which a star is so big that it can't get any bigger. Is there a limit to the size of a black hole?
So there's not really a limit because the size of the black hole is in a sense defined by its mass.
Right.
So if you make the mass bigger, so if you double the mass, you'll just like double its event horizon.
Right.
Did I say that right? Yes.
Yeah.
And so, in a sense, by putting more mass, you just make it bigger.
Yeah.
The things that are limited, so black holes basically have three properties.
Yeah.
Which is why they're kind of boring objects.
Right. So you get sucked into one. There's a point where it's not boring for a little while.
So there's the mass.
Yes.
There's the charge.
And spin.
And the spin. And so the mass, if you just add more mass, it just becomes more massive.
Yeah.
The size of the event horizon grows. But the spin is actually limited. Okay, so like if you try and increase the spin past a certain point, you won't be able to anymore because the spin is in a sense limited by the mass.
Right. Wait, spin, how is spin limited by the mass? How?
So in the sense that there's an absolute bound on how high the spin can be.
Why is that? Is that because of the speed of light? Why is or is it because it could counteract the gravitational
in a sense,
pull?
if you have this maximally spinning black hole and you try to chuck more stuff into it, it just won't go.
Oh, it'll just push it out.
Yeah.
Okay, got it.
So in a sense, trying to make these maximally spinning black holes seems to be fairly ubiquitous in the universe because when we go and measure the spin of black holes, a lot of them are very high spin. So you measure like spin in these absolute units. So like the highest it can be is 1, the lowest it can be is -1.
Yeah.
So it's like retrograde.
Yeah.
But a lot of them have spin like 0.9.
So when you eat the mass, I'm just going to use these layman terms. When you eat the mass of a planet or a star that comes by the black hole, you also eat its angular momentum, and that would add or subtract to the spin?
In principle, yes, but it's hard. So say you have like if I give a planet to the black hole, like it's hardly going to change its spin.
Yeah.
But if you have a more violent event, like say you merge two black holes,
yes,
in that way you can imagine growing the spin a lot. But in fact, if you have one of these mergers, it's not always clean. Like often you'll have a merger and the black hole will get kicked in some random direction. So you can bleed off angular momentum that way.
Yeah.
Just by having it, the merger product just like shoot off.
That's incredible. Okay.
So yeah, the physics of these kind of mergers is incredibly complicated.
Yes, and we talked about a merger when I went to go see. I don't know if you were there, but you invited me to one of the monthly talks they did at UNLV, where they talked about two supermassive black holes colliding with each other like 100 million years ago, and then
I totally forgot his name.
Gravitational wave.
He was a northwestern professor.
Yeah. Well, he was talking about the gravitational waves that were created from two. You know what? Let's back up real quick. For those of you who are listening to the word black hole and don't know what the fuck we're talking about for a second, we were talking to our producer Travis here earlier. Is that you, Travis? I don't have my glasses.
That is me.
That is you. Okay. Sorry, I was going to make sure I don't have my glasses on. We were talking to Travis before about acceleration, right? He was talking about acceleration in gravity, right? And when you have a level of acceleration, like on the planet Earth, acceleration is 9.81 meters per second squared. Well, just imagine that you continually increase that number until it got to 300,000 kilometers per second. Then that number would be to a point where light would not even escape. Is that pretty accurate?
So that's a good like hand wavy explanation. So there's a concept of like escape velocity.
Correct.
Which is like, so imagine you want to launch a rocket, right? So you're on the surface of the Earth and you want to launch off the Earth's surface. Mm-hmm. You're going to need a certain amount of velocity.
It's 11 miles per second on the planet Earth.
Okay. Yeah. So whatever that number is, okay, that will let you escape the Earth.
Right.
Now, a black hole okay, the escape velocity would be the speed of light.
Exceed speed of light.
Right.
Can the escape velocity exceed the speed of light, or does the event horizon just get bigger?
So in a sense, that's the physics is actually incorrect for that explanation, right? Because so suppose you don't reach the escape velocity at the surface. So say you launch off the surface at 5 meters per second or whatever the number is.
Yeah.
Okay. You can keep on adding velocity. You can keep on accelerating.
Yeah.
Right. And then you could reach the escape velocity eventually.
Yeah.
Right. But with a black hole, no matter how much you're accelerating, the whole way you won't be able to escape.
Correct.
And so it's a good heuristic. So like a good way of remembering, this is what a black hole means. If I had velocity equals the speed of light at the surface,
yes.
I wouldn't be able to escape using Newtonian physics.
Yes.
But that physics is actually not correct.
Because of relativity.
That's correct.
Because all right. So just to go back to what we said before, 9.81 meters per second square on the surface of the Earth because of the Earth's mass and how far away we are from the center. If you kept increasing that number to a certain point, you get to a point where no matter would be able to escape. And then at that point, light would no longer also be able to escape because you have bent space-time in on itself.
Yeah. So the picture that I have for what a black hole is.
Yeah.
So imagine one of these corn mazes.
Uh-huh.
Okay. So in a corn maze, right? There's if I go this way, I'll eventually get out. If I go this way, I'll reach the center.
Yeah.
Okay. Like a black hole is no matter which direction you go, they all lead to the center.
Yes.
That's the picture to have.
Yeah.
That it's not. It's like which way I go, how fast I go. It's no matter which way you go, how fast, you're just eventually going to reach the center.
Right. Is this? I know this is a weird question, but is that a function of gravity, or is that a function of space-time being bent in on itself, and no matter where you are, you end up back at the singularity, or is it both? Yeah. Or do we not know?
Okay. It's really the second.
Okay.
It's that no matter which way you go, you're going to end up towards the singularity.
Okay. And the singularity is the spot inside of the black hole that is hidden behind the event horizon that is infinite mass and infinitely small area. I forgot exactly how it's described.
Basically, so all this math that Einstein discovered to explain all these phenomena basically breaks down at the event horizon. So it's basically at the center of the black hole. You basically can't calculate things anymore with this theory.
Yeah. Okay. So we just don't know. Yeah. I had a professor one time that told me butterflies were inside of a black hole, and he was like, because we don't know. It's any guess is as good as ours because we don't know. Or the math breaks down, like you said before.
The math just breaks down, so you can't really calculate predictions anymore.
Okay. Interesting. Okay, awesome. And then what was I guess this is part of your thesis, the structure. What was the theory you came up with? What was your hypothesis from your doctoral thesis?
So the main thing I was working on were for these protostars.
Yeah.
So I was understanding how gas falling into the star affects gas that's being launched out.
Okay.
Okay. Because there's always this interchange. So we were talking about how angular momentum is conserved. Yeah. You can also kind of think of energy is being conserved in these processes. And so if some gas is losing energy and falling onto the star, other gas gains energy and gets shot out.
Okay.
Okay. And that gas that gets shot out, we can actually see it with telescopes. Okay. These are called winds. Mm-hmm. And the winds we can actually measure with telescopes. Okay. And compare to these kinds of simulations that I was doing.
And we're looking at, in this, we're just looking at protostars.
And this, we're just looking at protostars.
Okay.
Protostars are they're less cool sounding than black holes, but they're in a sense more cool because we have actual nice data. We can take pictures of these systems, and you can actually see the star and the disk edge on, and you can see the gas being shot out.
So let's talk about the future of that theory. The James Webb Telescope is going to be launched, I guess, in the next 30 days. Is that correct?
Week before Christmas.
A week before Christmas. Okay. Yeah. And the James Webb Telescope is supposed to functionally replace what the Hubble telescope is doing.
I feel that's a way to sell it to the public.
Yeah.
But I think it's really a different kind of machine. It's really, I think it is. It's going to be to study exoplanets.
Okay.
So the amazing thing. So exoplanets are planets outside of our solar system.
Yes.
So around other stars.
Yeah.
And what James Webb's going to allow is to measure the atmospheres of those exoplanets. So we're going to be able to see what kind of gases are on the planets outside of our
That's
solar
not
system.
really a telescope. That's like spectroscopy in order for you to be able to see that. Is that correct?
Yeah. So that's a
I said that word very weirdly.
Spectroscopy.
Spectroscopy, yes.
I mean that's a telescope technique.
Okay. So for people who don't understand, the Hubble telescope orbits the Earth. The James Webb telescope is going to be in one of the Lagrange points beyond the moon. Is that correct?
Yeah. So think of Lagrange points as like special points between like the Earth and so any two bodies are going to have Lagrange points.
Yeah. The Lagrange point is going to be a balancing act between two gravitational pulls, right?
Right. So if it like a simple way of thinking of it, if you have like two planets, there's going to be a special point where it doesn't know, am I getting pulled more towards this guy or am I getting more pulled to this guy? That's like a Lagrange point. And there's pros and cons of being at a Lagrange point. So the great thing of being at, I think this one's at L2.
Yes.
Okay.
So it's beyond, it's on the other side of the moon, which means we can't do repair missions.
You can't do repair missions, so definitely that's a downside. But once you get up there, it's going to be like reasonably stable place and be able to take good measurements.
Yeah. There's the Lagrange points trailing and leading the Earth, and there's like clumps of matter, like rocks that are trailing and following the Earth that are stuck in those Lagrange points. Isn't that correct?
So some of them are stable and some are unstable. So the stable ones probably have rocks.
Yeah, that's pretty crazy. Yeah, I loved learning about Lagrange points. It was pretty cool. I think where like you have gravitational pull from two different objects that like equal each other out. So you have a stable area to stay in. Very cool. So let's keep going about a couple more things. The gravitational waves. So this is something I've always wondered. The Neil deGrasse Tyson talks about this sometimes. A giant comes and just pulls the sun away, and for 8 minutes and 20 seconds, we don't see that the light is gone, and we are still orbiting a point in space that exists, even though the sun isn't there, because the gravitational pull from the sun still exists, or is still coming at us for another 8 minutes and 20 seconds. When you and I went to that one seminar where they were talking about those two black holes colliding into each other, they saw it and measured the gravitational waves at the exact same time, which would tell us that the speed of gravity is also 186,282 miles a second. Why is the speed of gravity the same as the speed of light?
That's a good question. I mean, wouldn't it be weird if it wasn't?
I mean, yeah, kind of, but
what? How fast would you want gravity to go?
I mean, I don't know. I mean, like we have all these other different speeds. I'm not sure. Like, so what? So whatever gravitons are.
So in a sense, right? If you start allowing gravity to travel at a different speed, then if it could travel faster, then you could definitely start having problems because you could probably communicate gravitationally. Instead of using light,
which kind of Interstellar was the movie was basically about.
Which breaks, it would start to break relativity.
Yeah.
So it definitely can't travel faster.
Yeah.
And then if it was traveling slower, I suspect that would give problems too.
Of course.
Yeah,
I just thought that was interesting. It's not something that you think about the speed of gravity, but that it does travel at the same speed as light. Because I thought that was interesting that we observed something the same time that we saw the gravitational waves change. When those two black holes collided with each other, it actually bent space-time in a very, very minor way that we were able to measure in. What were the two places that the LIGO thing is in Louisiana and Washington? I forgot where they were.
One's in Livingston. And, the detectors Livingston's in Louisiana. The other one's in Washington.
Okay. Yeah, that's pretty crazy. And
there's other detectors as well. Those are just the ones that are part of LIGO. Where do the other ones live? I think there's one in like Italy and I forgot where the other one is.
Yeah,
they're gonna put one in space too.
Oh yeah, that's right. They were gonna do one with two. Like they were gonna take 3 satellites and put them a certain distance away from each other, and they were going to make a LIGO detectors bigger than the planet Earth.
Yeah, so it's going to be called LISA.
LISA, okay.
And so it's basically going to be these 3 mirrors that basically are just floating in space, basically 5 million kilometers apart or something.
Wow, that's incredible.
Yeah, some huge distance.
Yeah,
and they're just going to measure the gravitational waves because basically what the current detectors measure are stellar mass black holes. Mm-hmm. So black holes that weigh as much as the sun or 10 times as much as the sun. But with LISA, you could measure mergers of much larger black holes, which that occurs at different frequencies. And so if you want to measure black hole mergers at different frequencies, you need like a different like baseline.
Yeah.
So you need like a much larger distance between the test masses.
Just for the layperson to understand, when you have we have two massive objects with their own gravitational fields and they collide with each other, the force is so massive it bends space-time. That's essentially that wave of the bending of space-time. Once it gets to us, that's what we're detecting. Is that correct?
So basically, the way a detector works is like it's called an interferometer.
Yeah.
Okay. So imagine like an L-shaped device.
Yes.
Okay. So you have a laser going like north-south, and then you have a laser going east-west. And so that laser, you split it so that one goes north-south, the other one goes east-west, and then you re-merge them together.
Yes.
Okay. Now, if the two arms are the same distance, when they merge back together, those two
now I understand.
Those two lasers are going to be in phase.
Yes.
Right. In the sense that they're going to merge back because light's a wave, and so they're going to merge like in phase. But if there's a gravitational wave that passes through the detector, it's going to make one of the arms shorter and the other arm longer, and so that when that light re-merges together, they're going to be out of phase, and that's
how you detect it. And we're talking about incredibly small amounts of shift.
Yeah, so
which is why you need that's why you need these detectors, these gravitational wave detectors, to be 5 million kilometers away from each other.
So you're talking like what they call like the shear.
Yeah.
Like the fractional change in length is like 1 part in like 10 to the 21.
Okay.
Okay, so like a billion, 1,000 billion
Okay.
times.
That seems difficult to detect.
Yes.
Yeah.
So like the hand wavy thing is like it's basically like the width of a proton for like an arm that's like 3 kilometers long, or
Got
4
it.
kilometers long.
What are some of the things that you are fascinated by now? That some new things in physics that are fascinating to you? That recent discoveries since you've gotten your PhD.
So in 1998, discovery of the accelerating universe.
Okay.
That's probably the most exciting thing.
Yeah.
Not figuring out what dark matter is.
Okay. And we're going to get to that. We're definitely going to talk about that.
I think that's another
That is
a huge problem.
You know, let's skip ahead. Let's talk about that. So dark matter, I think, is kind of a misnomer. I think maybe dark gravity would probably be a better way to name it, just because it doesn't interact with itself, or it doesn't interact with our matter.
So it only interacts gravitationally.
Gravitationally, correct.
Yeah. So here's like the basic story, right?
Yeah.
So one way of measuring how much mass is in a galaxy is just like counting how many stars there are, and then based on how many stars there are, you know how bright a star is roughly. Then you can estimate how much mass there is in the stars.
Right.
Then the other way you can calculate how much mass there is how fast the stars are orbiting in the galaxy.
Yes.
Right. So like say our like solar system, Mercury orbits around in less time than say Pluto.
33 days, I believe. Yeah.
I think I just made a misnomer there. I just called Pluto a planet.
Yes. Pluto is a dwarf planet because it is smaller than the total number. It is smaller than the mass of all the objects in its orbit.
I'm just a theorist.
Yeah.
So,
Okay.
So the point is that the further out you are, like the slower you orbit around.
Of course.
Okay. Now, if you look at these galaxies and you look how fast are the stars orbiting around, you can estimate how much mass is in the galaxy.
Oh, yes.
Okay. And that estimate of the mass is higher than the mass you get from just counting all the stars.
Counting all the stars. And,
So then-
and the planets wouldn't make up the difference either. That's not enough mass either.
The planets aren't going to make
Way smaller than stars.
Exactly.
Because if they were big enough, then they would conduct their own nuclear fusion and they would become stars.
Right. And so you arrive at this conclusion that, there must be matter that we can't see.
Yes.
Oh, let's call it dark matter.
Yes.
Okay, so they figured this out in like the 30s.
Yeah.
Okay, looking at these like so-called like rotation curves of galaxies. But then there was additional evidence that came about. So probably the strongest evidence was the bullet cluster. So you basically had like two galaxies that like slammed into each other.
Okay.
And when they slammed into each other, one part emitted a bunch of X-rays. Okay, but then that's one way of figuring out where the matter is, like where are the X-rays coming from. But the other way is you can use gravitational lensing. So basically, what Einstein figured out is that if you have a large mass, it bends space-time.
Yes.
And the light travels through this bent space. And so by looking at where the light's coming from, we can figure out where the mass is between us and the source of light.
Right.
And so if we do this for the bullet cluster, we realize that there's a whole bunch of mass, not where the X-rays are being emitted, but past beyond it.
Yeah.
So the picture that what happened is you had these two galaxies that have regular matter and dark matter, and they slammed into each other.
Yeah.
And as they slammed into each other, the regular matter stayed in the middle
Yes.
and emitted a bunch of X-rays, and the dark matter just went through itself.
Wow.
And now it's just like here, gravitationally.
So wait, so that would mean that our matter affects dark matter.
No.
No, it does not.
Like the baryonic matter, so the normal matter,
Yeah.
like the stuff we're made out of, it interacted with the matter in the other galaxy.
Yes.
When it slammed together.
So just so we're clear, dark matter interacts gravitationally with regular barometric. Was it baryonic?
Baryonic.
Baryonic matter, but it does not interact. Like we don't sense its matter, and it does not interact with itself.
That's right.
Yeah.
It doesn't interact electromagnetically,
Yeah.
so it doesn't emit light when it
Yeah.
interacts. But it's clearly there because we can detect it with the gravitational lensing.
We can detect it by looking at the gravitational lensing and looking at the speed of the rotation of certain galaxies.
Those are the two main pieces of evidence.
I have so here are the two theories that I've heard. And you tell me which one you like. The one of them
they're both wrong.
Okay, ready? The sexy one is this is gravity bleeding in from another universe into our universe. The other one that's less sexy is that this is just a force carrying particle we just haven't detected yet.
Okay, so to speak for the second one,
Yeah.
They've tried really hard to find the dark matter.
Yeah.
So like, okay, so we can detect it out in space. So we know there's some kind of matter.
But we're also in it. Like we're in it.
Right,
We are in a rotate. We are in the Orion arm of the Milky Way
Right.
galaxy. We're in it right now.
Look, so we know that it's out there.
Yeah.
But no one can like take a glass jar and say like, oh, here's some dark matter.
Yeah.
And so people have been like looking for it in that sense. So one way is they've tried looking particle colliders.
Mm-hmm.
So they try and create new particles using these particle colliders and see, okay, can we detect anything that might be a dark matter particle that has the properties that we expect it to have? They haven't found anything. And then the other way is we can just assume, okay, there's a bunch of dark matter out in space. Let's build a detector on Earth and try and like catch one of these guys. Because maybe they don't interact. Maybe they interact a very little.
Like what we did with neutrinos.
Exactly.
Yeah.
So what you do is you say, okay, let's go into like a mine. Okay, that's like 2 miles underground. So we block out all the other particles, and then let's put some kind of material that we think is going to capture the dark matter.
Yeah.
So usually it's some kind of like heavy inert gas, like xenon or
Yeah.
something. And so you build this big tank of xenon. And so at first they started modestly. They're like, okay, let's start with like 10 kgs of xenon.
Yeah.
Didn't detect anything. So they're like, all right, let's try with 100 kgs.
Yeah.
Still didn't detect anything. All right, let's try a ton.
Yeah.
Still nothing. And now they're trying like a few tons. Still didn't find anything. So like at this point, it's not like fruitful anymore.
Yeah.
And so they really need like a new kind of way of looking for it.
It's crazy. This is this incredible thing that affects it's the majority of the mass of the solar system, or I'm sorry, the solar system of the galaxy, and we don't know what it is. We have no clue what it is.
So based on cosmological observations,
Yeah.
there's like 5 times as much dark matter as baryonic matter
Yeah.
by mass, and literally don't know what it is.
So dark energy, which I believe the Nobel Prize for dark energy was like 2011, I think, is when it was awarded, and that was the idea of, is that the reason for the expanding universe? Is the dark energy?
So if we look out in space, we
Yeah.
see all these like galaxies that
Yes.
are receding away.
Yeah.
So think of it like a movie. If things are receding away now, you can play the movie backwards.
And then that's where we get to that.
And then everything's going to come in, and then at one point you're going to have this like singularity, and we call that the Big Bang.
Big Bang, right.
Okay, so one of the things Einstein discovered is his equations describe how space expands based on what the matter is. So imagine an equation. The left-hand side tells you how space is curved. The right-hand side tells you what's the matter content. And so if we know how space is expanding by looking at like how the galaxies
And this was Edmund Hubble who first discovered this, correct?
Yeah, so he's the one who first
He discovered this and made some pretty fucking crazy comments also. Like don't look at Edmund Hubble's past. Anyway, go ahead.
Yeah, so if we know how things are receding,
Yeah.
then we can figure out what the matter content
Right.
is. And what we do is we get basically realize that the different kinds of stuff dilutes at different rates. Okay. So like normal matter is the easiest to understand.
Yes.
So imagine we have like a certain density of gas in this room. Okay. Now imagine we double the size of the room in all the dimensions, right? Double the length, double the width, double the height.
Okay.
What's going to happen to the density?
It's going to go down by if we double in all 3 dimensions, we would be 2 to the 3rd power.
Right.
So 16. 1/16 as much.
2 to the 3rd, so 8.
8, sorry, my bad.
Okay.
1/8.
So that's how normal matter dilutes.
Yes.
Now, radiation dilutes by a factor of 4.
Okay.
Instead of a factor of 3. The reason is you get that dilution effect. Like there's less in the volume, but also the photons get redshifted. Okay. Meaning their energy drops. So imagine like a photon is a wave. Yeah. If I double the size of the room, I am also doubling the wavelength of that light particle, and so its energy goes down.
Yes.
Okay, so that's why it dilutes like a factor of 4. Now, dark energy is this mystical constituent of the universe.
It never dilutes.
It never dilutes.
Okay.
So if we have a certain density of dark energy in this room, if we double the size of the room, the density of dark energy stays constant.
Wow.
Which that's in a way that's really weird, because then the total amount of energy in the dark energy has increased.
Yes, it consistently increases, which that doesn't make sense, but it makes sense.
Right. And so that's basically like the defining property of dark energy, and we basically don't know any of its other properties.
Okay, so let me ask you, Einstein's cosmological constant and dark energy, did they have something to do with each other? Like accidentally one measured the other?
Well, so the cosmological constant is just a constant that you could put in Einstein's equation. Mm-hmm. And what did I just describe? I just described, it's this energy that no matter what happens to the universe, it stays constant.
It's constant, got it.
And so it's just this thing that also has the same property. And so then you can get into this idea of like the cosmological constant problem. So in quantum mechanics, one of the like key features is if you have a quantum system, you have like a ground state, meaning that your system is going to have some minimum energy that it's just the minimum energy that you have just because this system exists.
Right.
Okay. And so you can use quantum mechanics to calculate, if I just have a box, what's the like energy to put a quantum field in this box? Okay. And you'll arrive at some answer. Now that answer is much less than the let me get this wrong. It's 120 orders of magnitude off of what you need to be able to describe the dark energy. Okay, so when we use regular conservation of energy, regular Newtonian physics, all this kind of stuff, this does not describe this energy source that seems to be abundant and constant and infinite and goes on forever and continues to expand the universe. Okay, so conservation of energy is actually a misnomer. So you actually don't have conservation of energy in a general system with general relativity. So the like technical kind of like reason that's not so hard to understand, like energy conservation means that your system has a symmetry in time. So you can go forward in time or backwards in time, and there's a conserved quantity. And we call that conserved quantity energy. Now, in what Einstein taught us is that you're basically free to label space and time however you like. And so in a general space-time, you can't just like label a certain direction as time, because then you'd have that like preferred direction. And so because you don't have that in general relativity, you don't have conserved energy. It's actually that kind of concept breaks down. Okay. So the problem with dark energy is actually not that the energy is not conserved. It's just really like what is this thing? And it's funny because people write in their like grant proposals, they're like, I'm going to study like dark energy with this like telescope, and they don't even know what they're doing. Like no one knows what this is. But at the same time, I think it's like the most exciting problem. Like, everyone should be working on this or dark matter.
Amazing. Can we do some astronomy 101 stuff here for the audience? Okay, let's do some. Let's just go through three things real quick: Newtonian physics, relativity, and quantum mechanics. Let's just go through those 3 things, and then at the end, we're going to compare and contrast and figure out why relativity and quantum mechanics don't fit together, right? So real quick, Isaac Newton lives in the 16th century. Is that correct? I believe that's right.
Oh, you got to look at these things.
Yeah, I keep forgetting. I'm sorry. I knew this before. But anyway, Isaac Newton, maybe the smartest man who ever lived. Two things. Before he turns 25, he looks up at the moon and he says, if an apple falls from a tree, does the moon not also fall? And he looks at the moon and he's like, well, what if the moon is falling towards the earth and it actually has like a lateral movement also that's canceling that? And then he comes up with this idea for an orbit. But at the time, there is no real way to measure a curve like that would be necessary. So Isaac Newton at the age of 25 invents differential calculus. Am I right so far?
Other people worked on it as well, but
yes.
he wrote it down himself.
Correct. Yes. Yeah. So he comes up with this idea for differential calculus, and then from that he writes a book called Principia. And the thing about Principia that's so amazing is that he doesn't really have. At this point, there are telescopes because I believe the telescope was perfected. The modern one was like 1601 by Galileo.
Okay, Galileo had a telescope.
Yeah. So he comes up with these the things about Newtonian physics. Two people that I've always been fascinated with are Charles Darwin and Isaac Newton. The reason why is because when you go read On the Order of Species by Charles Darwin, he comes at the end of the book and he starts talking about everything coming from one cellular object. He theorizes without the ability of understanding any of modern biology, comes up with a correct answer for where all of life came from. To me, that is one of the most genius for him with completely limited information to come to that hypothesis, which turned out to be completely correct, is absolutely fucking incredible to me. The idea that Isaac Newton came up with the idea for how orbits were to work. Well, obviously he knew somewhat because his calculations for gravity came from Johannes Kepler. But the idea that he understood, hey, if I have an object and I go far enough, it's going to go in an orbit and come back. And that also we use some of the calculations in there. For instance, when we build Resorts World, the casino over here, we aren't using relativistic formulas or quantum mechanic formulas. We are using Newtonian physics in order to determine how much structural strength we need in order to build a building that's 800 feet tall, right? We're using Newtonian physics. So the idea that he got so much of this correct, not understanding things like absolute zero or deep space or the fact that the atmosphere is 60 miles high, any of these things, not understanding what gravitons are, not understanding electromagnetism, not understanding the strong nuclear force or the weak nuclear force, not having any idea of any of that. For him to get so much correct in the 16th century is, to me, is one of the most fascinating things ever. We still use those formulas.
So one, it's inspired.
And also he had Asperger's disorder and he died a virgin. But keep going. Go ahead.
One, I think it's inspiring, right? Because it means that if you people make excuses, right? Like, I don't have like all the tools, right? And instead of just thinking like, maybe the tools I have is good enough, right? But I think what you're kind of alluding to is actually like a deeper concept in physics. This idea that like every theory is going to break down, but where that theory breaks down, and also having an understanding of where that theory breaks down is very important, right? Now, it turns out that Newtonian physics breaks down once you start going at the velocity of the not even acceleration, once you start going at the velocity of the speed of light.
Well, no, it breaks down before that, right? I mean, you start having time dilation at 86% the speed of light. You're half time dilation.
Yeah, you don't have to go like at 99% of c.
Yeah,
but you have to be going a fraction of c.
Even 1% c, you would start seeing like some pretty massive differences.
Things would be measurable, but like 1% of c is so like fast in our everyday experience that theory is basically not going to break down.
Correct. Yeah.
Right. And so that's really like the crux of it, right? Is if you want to do good physics, you just have to, whatever theory you write down, you have to have an understanding of when it's going to break down, and just make sure you stay out of that regime.
So Newtonian physics is going to break down when we get to like particles that are in superposition, and Newtonian physics is going to break down when we get to acceleration. That's like, for instance, there is a small correction you have to do with satellites, GPS satellites, because they are in a different, they are experiencing different acceleration than we are on the surface of the Earth.
So things are going to break down at small scales. So quantum particles have this like uncertainty.
Yeah.
Okay. And the way to think about that is at small enough length scales, things start to behave both like a particle and a wave.
Yeah.
Okay. And what characterizes the wavelength of a particle is its de Broglie wavelengths.
Yeah.
Sometimes pronounced de Broglie.
Yeah.
And so as long as you're much larger than the de Broglie length,
you are a macroscopic quantum object, and all your particles are in phase.
There are certain exceptions, right? So remember we were talking about like the LIGO detector?
Yes.
So those mirrors, they weigh like 40 kg.
Yeah.
Okay. But they're actually in this like quantum state. And that's why it can detect, such small oscillations. So it doesn't mean that just because the thing's, weighs like tens of kgs doesn't mean it's not a quantum.
Got it.
Behave like a quantum particle, right? But like hand wavy, that's roughly correct. Okay, and so as long as you stay away from that really small regime,
yes,
and that really fast regime,
yes,
then
the Newtonian physics
Newtonian's pretty damn good. Yeah.
Okay, so the three laws of motion.
The way people used to formalize things like back in the day was actually really weird.
Yeah.
Right. Like the way you like learn physics, like the modern way.
Yeah.
Was more like in terms of like equations and like concepts.
Yes.
But you don't like write these elaborate statements in your Principia or whatever book you write. You know?
Yeah, pretty crazy. Okay, so now we got Newtonian physics.
That covers Newtonian.
You guys live in Newtonian physics. Pretty much most of the stuff that we deal with the Newtonian physics. There's a couple of exceptions, like we talk about with GPS satellites or the orbit of Mercury. There's a few things that are different. There's a couple, like you talked about gravitational lensing, which is how we proved relativity in 1919 when they looked at a lunar eclipse or solar eclipse. So there's a few instances of relativity in our lives, and then there's a few incidents of quantum mechanics in our lives.
There's a lot of incidences of quantum mechanics
with transistors and
we
lasers.
just don't. They're just working under the hood,
right? With quantum mechanics, for a quick and dirty, for a girl who was working at the Rhino and just got up at 5 o'clock and just got home and is watching this podcast. Quantum mechanics.
So quantum mechanics is what lets the computer chips in your phone that lets you surf Instagram.
Yeah,
that's what lets you work so well.
Just an explanation.
Yeah. So it's basically the physics of really small particles, so like individual electrons and how they interact in like a metal, for example. So if you understand like semiconductors and like metals, you're going to need quantum mechanics.
Okay, and then just the mystery of it, of the idea of things like superposition and collapsing into one position.
So the hallmark of quantum mechanics is that you can't ask all the questions that you might want to ask in classical physics.
Right.
So in classical physics, it makes sense to ask a question like, okay, where is Michael Sartain?
Yeah.
What is Michael Sartain's momentum?
Right.
Okay, those are like fair questions to ask. But if you were a quantum particle, you can't actually simultaneously measure
both
your momentum and your position.
Got it.
You have to measure one, and whatever uncertainty you have in your position, that's going to tell you a minimum amount of uncertainty you have on your momentum.
Yeah, just a real quick note for those of you who watch Breaking Bad. You know where I'm going with this.
No, I don't.
The main character his name is Heisenberg, and the reason why is because his enemies did not know what he was doing, and he is the individual, the doctor, who came up with the idea of the uncertainty principle.
I didn't know that.
You didn't know that? Yeah.
No, I didn't know that about
Walter White. His nickname when he was cooking meth was Heisenberg because he came up with the principle of uncertainty.
I don't watch TV.
Oh, okay, sorry. You're a theoretical physicist. It's not like Sheldon Cooper. You actually you don't have time to watch TV. Got it. Okay.
So that's quantum mechanics in a nutshell, and so quantum mechanics becomes important when the uncertainty in particles' position becomes comparable to the size of the system.
Yes.
Right. So a hallmark of these quantum particles is that sometimes they behave like a particle and sometimes they behave like a wave.
Yeah.
Okay. So probably the most famous example is this like double slit
when
experiment.
When was the first time they did the double slit experiment?
I think in like the 1800s.
Is it?
Yeah.
Wow, incredible.
Hey
guys, if you guys want to take a second and hit pause and go look up the double slit experiment so we can understand the mind fuck that is, you want to go ahead and do that. Go ahead.
So I want to say it was in the 1800s because it was Young who did this, Young's double slit. And so the basic idea is you have some light source and then you pass that light source through two slits.
Yeah.
And what ends up happening is at the time people thought like, oh, light's probably a particle.
Yeah.
But what they found is that if you put a screen far away from the slits, there would be like dark and light fringes. Mm-hmm. And the way that was interpreted was that's the same as like if you imagine you pass a bunch of like waves through like you have some like buoys on a dock. Okay, basically they're going to be passing through this like wall, and those waves, as they pass through the wall, they're going to interact with each other.
Yes.
So the waves through one slit are going to interact with waves through the other slit, and in some places they're going to add constructively.
You're going to get what's called an interference pattern, which is going to be light, dark, light, dark.
That's right. That's right. So the light is where you get like two maxima of the wave, and then the dark spot is where you're going to get a maxima and a minima, and they cancel out.
Got it. And
this was seen as like, oh, this must be evidence that light is actually behaves like a wave.
Yeah.
But then the subsequent experiments were even like more wild, because then what they started doing is they started like firing like individual electrons.
Now, this wouldn't be in the 1800s.
No, this was not in the
Yeah.
1800s. This was I mean, much later. But yeah, you'd fire like individual electrons, and that individual electron would interfere with itself.
Yeah.
Which is crazy, because if you think of an electron as a particle, you'd think, okay, it either went through one slit or it went through the other. But in fact, from doing this measurement, it's going through both,
Yeah.
interacting with itself and making this like interference pattern.
Yeah.
But then it gets even crazier, because so if you put a detector at each slit and you actually turn the detector on and you measure, oh, the electron went through slit 1, well, then it stops interacting with itself.
Okay, so now here's where this is the part where the mind fuck kind of did make sense to me. I use a detector. The detector does not have to be a human eyeball. The detector
No,
just has to be
some mechanical device.
mechanical device that measures photons. Okay,
Yeah, that's right.
All right. So now I'm sitting there doing this, and when I turn it on, I'm not getting an interference pattern anymore.
That's right. The interference pattern will
I
actually
want to
turn on.
see this. Like, I literally want to see somebody turn on the thing, and then all of a sudden, whoop, all of a sudden I can see, instead of seeing, just break it down. We're firing photons through one slit. When we fire it through one slit, we have one line behind it. When we fire it through two slits, what we should get is, I'm sorry.
Like if it was like classical,
Yeah, classical physics.
Some photons would go through slit 1, some would go through slit 2. So you'd have two bright.
You'd have two bright lines. Instead, what you have is what's an interference pattern, which is light, dark, light, dark, light, dark, which doesn't make any sense unless those photons are actually waves. They're not actual particles, and they interact with each other like waves. And that's where it's crazy. And then you observe it. You, like you said, you use a detector, and now it goes back to two slits, actually two lines. And the act of observing it actually caused it to collapse into one. Instead of being in superposition, to collapse into one reality or one position, if you will.
Because in a sense, what you did is you asked the particle, where are you?
Yes.
Right. And then the particle's like, oh, I'm in slit 1.
Yeah.
And so the universe has to be consistent in a sense.
Yeah.
And in achieving that consistency, if the particle said I'm at slit 1, then it's going to make on that screen as if it went through slit 1.
Yeah.
Well, it has to be a consistent
now
picture.
This is where things get weird, because now we're going backwards in time to determine whether or not it went through slit 1 or slit 2. There's one study that I heard about. If you were to observe light that was in superposition coming from a star, and once you observe the light, now the light collapses into an actual position, but it has to go backwards in time through all the way back to Proxima Centauri, that's 4.1 light years away. There's some weird phenomena that doesn't make sense with entropy.
No, so okay, at first this is like confusing,
Yeah.
but the way to think of it is just think that the universe has to be consistent.
Yes.
Okay, so at first you think, okay, there has to be this like spooky action at a distance,
Yeah.
right? You think, okay, I measured, this particle, and now the star has to know about it.
Yeah.
And so the signal has to travel all the way back.
Yeah.
But in a sense, the universe, like, it already knows it shot this photon
Yeah.
towards you. And so it doesn't have to like communicate it back. It in a sense already knows. It's just the story that it tells has to be consistent.
Yeah.
Right? So it's like if you have these so in quantum mechanics, you can have these like coupled particles.
Yes.
And so like for people watching at home, so just imagine these quantum particles have this property called spin.
Yes.
Okay.
Maybe two electrons from the same atom.
Yeah,
Would that be-
like two electrons, let's say. Well, you create these two particles, and they have this property that whatever spin particle A has, particle B is going to have the opposite spin. Okay? That's the only way they can be created self-consistently.
Got it.
So now we put them in a box. You take yours, you go
To one side of the universe.
one side of the universe. I keep mine here. And then one day I decide I'm going to open the box and I measure the spin. Mine say up, spin up.
No matter what my spin is, it's going to be the opposite.
Your spin is going to be down.
Yes.
Okay. Now, some people, it's easy to interpret this as, there had to be instantaneous communication.
Right, which would be faster than light.
Which would be faster than light.
If I'm on some other part of the
Right.
world.
But that's not the right way to like think about this. The right way to think about this is initially when we created those particles, they were in the same place, and so they could communicate with each other.
Yeah.
And they have this property now that they're coupled.
Yeah.
And now we separate them, no big deal. They've already established that they're coupled.
Yeah.
And so there's no spooky action at a distance.
That's interesting. It still does seem like it.
It's literally just that the universe has to have this consistent story.
Right.
Okay. That's the way to think of it.
Okay. Beautiful. So we were talking about, we got through in quantum mechanics, we talked about once we get to microscopic quantum objects, they act as a particle and a wave at the same time. When we observe them, then they collapse into one thing. Something about taking particles down to near absolute zero, we can observe certain phenomenon. Is that true?
Yeah. So, okay. So what does temperature mean?
Temperature is particles interacting with each other that creates. There would be no temperature if it was just like one particle by itself.
So think of it as like temperature is like particles like vibrating.
Yes.
Okay. And so if we imagine if we want to like cool things down, what that means is we're slowing down those vibrations.
Yes.
Okay. And so what you could imagine is at one point you're slowing the vibrations down such that the vibrations are roughly the size of like how big those quantum measurements are. And that's really when we start entering that like quantum regime.
Yes.
And so when you're like near that absolute zero,
so that's negative 273.2 degrees Celsius. Is that correct?
It's like hella cold.
Yeah. Right. It's or 0 degrees Kelvin.
Yeah. So that basically means that the particles don't have any more jitter.
Yeah.
Okay. And we know from quantum mechanics that they have to have some jitter.
Yeah.
Right. Because otherwise we would know precisely where they are.
But now it's becoming measurable almost.
And so it becomes harder and harder to like cool them down.
Yeah.
And actually it's really weird. Like the way you cool them down typically is with lasers.
Yeah. That is weird.
Yeah. So, you have these like particles and you shoot a laser through and you tune the laser such that it's just like extracting away those like last bits of
okay
energy.
Oh, I did not know that because I know
it's this entire field called cold atoms.
there's something that I read somewhere. There is a laboratory here on Earth that was the coldest place in the universe. They got closer to absolute zero than any place in the entire universe by sucking the energy state out of some area.
I don't know how they did it, but probably with lasers.
Yeah.
So the point is that like as you cool things down, they start to behave more and more like quantum particles because you reach that like quantum limit.
Yeah.
And what's really interesting is if you cool them down sufficiently, you can get large collections of atoms behaving like quantum particles. So usually when you think of quantum mechanics, we think, oh, this is like what describes like a few particles. But by cooling them down, you can actually get many particles all collectively behaving like one large quantum particle. So that's what they call these like Bose-Einstein condensates.
Okay.
So this is what they won the Nobel Prize for, I think in 1995.
Okay.
So it's predicted by like, I guess Bose and Einstein way back in the day. And like 100 years later, they managed to achieve it in the lab. So now they can just like study these systems because it's like, think of it like it's hard to study just like one atom. It's really small, but imagine now you have like thousands of atoms that behave like a quantum particle. It's much easier to study.
Yeah.
And so the people who study quantum mechanics now, it's with these systems.
That's incredible. Okay, but by cooling them down as far as you can, to come
right.
to things that make it a little bit easier to measure because it's not vibrating as much.
That's right. And they can do all kinds of things with like small collections of atoms. So like you can study what happens at like incredibly high pressure.
Yeah.
So that like we were talking about metallic hydrogen.
Yeah.
So they think they made metallic hydrogen. The basic setup is like you take like two diamonds, make them really smooth. You throw in a bunch of like hydrogen in there and you collapse the shit out of it.
Oh wow.
And then you try and reach like a high enough pressure to try and reach like a new state of matter.
Incredible.
Right. So like when we think of like water, right, there's like three states, like gas, liquid, solid. But these other systems, they can in fact enter like new phases, and these new phases are going to have like new properties, and this will like really like cutting edge physics because this might lead to like new kinds of like consumer electronics, might lead to new kinds of like fuel for like rockets, all kinds of like
that's incredible
stuff.
Yeah, new states of matter for that's amazing. That's incredible. Hey, I got a trivia question for you, Travis. Ready?
All right, I'm ready.
If I if I take ice from, I already gave it away. If I take ice from a solid state to a liquid state, what's that called?
Melting.
Okay, we go from a liquid state to a gas state, what that's called?
Evaporation.
There we go. If we go from a gas state to a liquid state, what's that called?
Condensation.
Very good. When we go from a liquid state to a solid state, what's that called?
Freezing.
Very good. Now, ready? Here's where it gets tricky. If we go from a solid state to a gaseous state, what's that called?
Sublimation.
Sublimation. And when we go from a gas state to a solid state, what's that called?
Vaporization.
No. Oh. No? It's called deposition, and I didn't fucking know that until a couple of days ago. I looked that up.
I'm surprised I was able to answer all those.
It's called deposition. I had no idea. I just looked that up the other day. Cool. So yeah. So talking about that, when we go to in quantum mechanics, you talked before about transistors and or not transistors, but lasers and stuff like that. Can you explain? So we just talked about the wave particle duality. Now, how does that get us into lasers and modern technology?
Well, I mean, lasers is one example, right? So lasers are based on quantum principles.
Yeah.
And so like think of everything that has a laser in it. Like there's innumerable amounts of electronics. Transistors, like the thing that's letting, like Moore's law, for example, the prediction that
every
basically processors,
months.
Every 18 months doubles in speed. We're very close to the quantum limit. And so if we want to keep on improving that, we're gonna have to understand these kind of like quantum processes.
Okay, so actually, let's go back to something else you said before. These two particles were entangled, right?
Yeah.
And so they kind of, because they were entangled, they kind of knew or had an arrangement beforehand. When you looked at one, you saw the other. Wouldn't that make the quantum computing theory, the idea that we'd have a computer on Mars that would instantaneously be able to communicate with one on Earth, wouldn't that kind of throw that theory out the door if we've already predetermined the spin of the two particles?
So in a sense, well, I'm not sure if you can actually make some algorithm to use to communicate. Like,
right.
It's cool to know, you have a spin-up particle.
But you understand
like, what does that help me?
Yeah.
Like, so you'd actually have to create some kind of communication protocol that uses, because you can imagine like I give you a bunch of entangled particles.
Yes.
You go to Mars and then I have my own box of entangled particles. If we had some communication protocol,
we'd have FTL with faster than light ability to communicate with each other. Because I'd be able to, because even if it's ones and zeros, every time I get up, you get down. Every time I get down, you get up. If I could communicate with you in that way, then what would happen is I'd be able to send you messages, communicate information to you faster than the speed of light.
So I just want to emphasize that you're not breaking any laws of physics,
right? Because
we spoke to each other beforehand, right? And physics just says that if you haven't spoken beforehand, you can't communicate at faster than light.
Got it. Okay.
But we can't, if we contrive to have entangled particles, then we're not really breaking that bound.
I get what you're saying, but not really. I kind of understand that. And I read an entire book about this, and I couldn't really understand. Like it's almost predetermined that because your particle is going to be spinning upwards, or you're going to have an up charge, I'm going to have a down charge.
Okay, so look, think of it like this, right? Mm-hmm. So imagine we agree right now that on a 5-digit number, okay, and now you go and drive off, and some police officer like stops you and he asks you, or he stops me, and he asks me like, oh, what's the 5-digit number? And I like tell him, right? Just because I know what your 5-digit number was doesn't mean that I was like speeding away at like a certain like speed,
right? Or
because we'd already contrived.
It doesn't mean that the information was actually traveling faster. I think I understand now. Yeah. That makes sense. All right. So how does that? The lasers are a bunch of things in phase. Like what is the quantum? Like what is from quantum mechanics that leads to modern electronics?
So what you have in a laser is a quantum system. So the most basic quantum system, you have a ground state.
Okay.
So that's the system when it has the lowest energy.
Okay.
And then you have excited states.
Yeah.
Okay. So like you have like put 1 unit of energy, you're going to be like 1 level of excitation up.
Yeah.
Put 2 units of energy, you're going to be 2 units of excitation.
This has to do with the orbits of the electrons? Is that the same kind of?
That has to do with the orbits of the electrons.
And when it goes from one state to another, it doesn't like increase altitude like an airplane does. It just disappears from one.
It's either 1 or 2 or 3 and so on.
It's weird. So that's what you're talking about. It disappears from one and then just reappears in the other state.
So the way a laser works is there's some kind of like inversion process where instead of being on the ground state, you excite everything up to the first excited state, and then it drops back down. And then when it drops down, it emits a photon.
Okay.
And then that photon has a fixed frequency.
Oh, wow. Okay.
So it it's basically that's why it's like a fixed wavelength.
The photon is the energy from the
it's the little light
excitation
particle.
state
It's the
leaving.
light
Got
it's the
it.
light particle that gets emitted when you drop down states.
Okay.
And so that's why you have this very like constant, source of photons in
Okay.
a laser. Yeah.
All right, went over Newtonian physics, and then we hit quantum mechanics, and now relativity. All right, matter tells space-time how to bend. Space-time tells matter how to move.
So let's draw the distinction between like special relativity,
Okay,
and general relativity.
Okay.
So special relativity, I think, is easier to understand.
And that was Einstein in 1910.
05.
05, and then
yeah.
the second one was in 15,
Yeah.
and then photoelectric effect was in 1921. Or no, he won the Nobel Prize in 1921.
Yeah, he probably did the photoelectric effect in 1905.
Okay.
That was his he had this mega year where he
Okay.
came up with Brownian motion
Yes.
that helps you trade
Well,
options.
The botanist
And,
the botanist Brown actually came up with Brownian motion, but yes, he attributed it to physics.
Yeah, and then special relativity, and I think the photoelectric effect.
Yeah.
was all
But a lot of people don't realize this. He did not win the Nobel Prize for relativity. He won the Nobel Prize for the photoelectric effect in 1921. Even
you have to look that up.
though relativity was proven in 1919, because it was during World War I when they actually looked at the lunar eclipse, and I was able to see the gravitational lensing of the stars around the sun, which proved relativity. Anyway, go ahead. Sorry.
So the two tenets of special relativity is that the speed of light is constant.
Yes.
And basically nothing can travel faster than the speed of light.
Yes.
Okay. And all observers are going to agree on what the speed of light is.
Yes.
So that's completely different from classical physics. So say you're driving your car at 50 miles an hour.
Yeah.
I'm driving my car at 40 miles an hour. I'm going to see you going away 10 miles per hour.
Yeah.
Right. You're going to be gaining 10 miles per hour on
Yes.
it. Now, if replace me with a light beam, right? If I'm shooting down at the speed of light, Travis measures me at speed of light.
Yeah.
You measure me at speed of light, even if you're going 50 miles per hour in your car and Travis is on the side
It's
of the
not
road
speed of
watching.
light plus or minus 50. It's
That's
always
right.
300,000 kilometers a second.
Exactly.
Yeah.
And so this leads to all kinds of wild effects. Okay, so one of which is time dilation.
Yes.
So if you're in a rocket ship going really close to the speed of light, time is going to slow down for you. Okay, and so this sounds like a wild thing, but it's actually been measured with planes. So they take an atomic clock, they put it on a plane, they take the other atomic clock, they leave it on the ground, they fly the plane around the Earth a couple of times, and they compare the difference in time, and there is a time difference between the two.
Yeah.
And so like you were alluding to before, this is super important for GPS.
Satellites, yeah.
Yeah, so satellites require very precise clocks, and for the GPS to work correctly, so to be able to locate you on your phone down to meters,
Yeah.
you need special relativity to be taken into account.
You have to take into account because the satellite is in a different part of the gravity well than we are.
So that's a general relativity effect.
Yeah.
So we'll get to that.
Okay.
So you need to take into account special relativity because the satellite is orbiting around at such a high velocity that special relativity becomes important.
So, okay, got it. Yeah.
Yeah.
And by the way, going back to what you said before, the escape velocity for the Earth is 11 miles per second, but to get to orbit, it's 5 miles per second.
Okay.
17,500 miles an hour.
Right. This is the difference between getting to orbit and getting escape
Exactly.
velocity.
There's a lot of
Yeah.
people get this confused because they thought that when we had the SDS program, we were going to space. No, we were going to low Earth orbit. We were not. It's not. We did not quite exceed the Earth's gravity, but what the Apollo missions did. Anyway, go back. What you're saying?
So what general relativity is saying is that there's no difference between a gravitational well and an acceleration.
Yes.
So imagine you're in a rocket ship with no windows, okay, and you feel being pulled down, okay. In a sense, you don't know whether your rocket ship is on Earth and you still feel Earth's gravity,
Yeah.
or if you're in the middle of space and the rocket's accelerating forward
Yes.
at the same acceleration as
Correct.
you'd feel on Earth.
Yeah.
That's the crux of general relativity.
Yeah.
And so if we want our satellites to work correctly again, the satellite that's orbiting on Earth is less deep in the gravitational well
Yeah.
than we are on Earth. And so we want to take into account that different gravitational effect so that we can again pinpoint our location.
Time is traveling slower for us because we're closer to the well. It's traveling faster for the
That's right.
satellite
That's
with
right.
respect to us.
That's right. So they're actually on opposite effects, and they're actually very close to each other in order of magnitude.
Yeah.
So yeah, because we've discovered special and general relativity, our GPS works
Right.
amazingly well.
Okay, so now the other part about I know that the orbit of Mercury was one of the reasons why Einstein came into the idea of relativity. What exactly is unique about the orbit of Mercury?
So Mercury has what they call like a perihelion shift.
Okay.
So the way to think of it is like there's like a precession of the orbit.
So the orbit, instead of going just like this, and it goes the oval starts to shift. Is that what you're saying?
Yeah. So the oval starts like shifting around like that.
Oh, wow. Okay.
Okay. But this effect is like incredibly tiny.
Yeah.
Like you're talking, I'm trying to remember, it's like 40 arc seconds per century or something.
Okay.
So there's like 360 degrees.
Still a couple hundred miles, you know.
Right.
Yeah.
Well, just in terms of like degrees in the sky, it's
Yeah.
just incredibly small.
Yeah.
And yeah, if you take into account various like classical effects, you can account for some of that shift, but you really need general relativity to be able to explain the biggest contribution.
Yeah.
which is due to GR effects.
Yeah.
So yeah, those were the basic classic tests. So that was a post-diction. Like people had already measured this, and they were like, "Why is there this shift we can't explain?" So Einstein was able to explain it. It's not as impressive, right? Because it had already been measured.
Yeah.
But the gravitational lensing was entirely new prediction.
Yeah.
And that came out perfect. And what was the last test? It was like another classic test. I can't remember.
But his belief about gravity is where we come up with the idea for black holes?
Yeah.
Or
So
we're able to describe black holes?
So using his formalism, you
Okay.
can go and explain black holes.
Because one of the things you just mentioned earlier is gravity and acceleration are the same thing.
Yeah. So that's more of a philosophical realization and a way of explaining this like simple picture of like the rocket ship. You don't know whether it's accelerating or whether it's on Earth. Okay. But that kind of like philosophy went into the mathematics that explains general relativity. So it goes into the sense that, so philosophically, right, Newtonian physics, there's a distinction between space and time, right? Space is like the playing field, and like time is the parameter that we measure,
Right.
that we're like going forward in this playing field. In general relativity, there's no distinction essentially between space and time.
Right.
There's no difference between a stopwatch and a meter stick.
Okay.
In a sense, we just decide meter sticks go this way, stopwatches go that way.
It's just a fourth dimension.
It's just a fourth dimension,
Yeah.
exactly. And so is that like philosophical shift that we should like treat them on equal footing that lets you like write down these equations.
So go ahead.
Yeah, so what comes about from this equation is the Einstein equation, which, like I was describing earlier, the left-hand side describes this is how space is curved, and the right-hand side describes this is the matter content. And so there's kind of like two ways of thinking of this equation. So one is, if I tell you how space is curved, you can tell me what the matter content is. That's what we do in like cosmology. We
Yes.
look out, we measure how are the galaxies receding
Which is
away.
where we determine where dark matter came from, because the math didn't add up.
Or the dark energy.
Yeah,
That's
dark
right.
energy. Yeah,
That's right.
dark- yeah.
And then the other way is, if I give you the matter content, then I can tell you how space is curved.
Curved,
And
okay.
so that's how black holes come about. So with a black hole, you say, suppose there's no matter content, and you make the simplest assumption. You're like, okay, let's assume we want a system that's like spherically symmetric and stationary in time. And you're like, right, try and solve this equation. And that's what Schwarzschild did.
Yeah.
in, I think 1915. And he came up with this black hole solution. And then people kind of like, from knowing how space was curved, calculated what are the properties of this object, right? And they realized, oh, there's this thing called like the horizon, and there's a singularity at the center, and in a sense it was very like theoretical kind of concept up until progress was made like in the 60s and 70s.
So you could theoretically, if you compress the matter of the Earth into something the size of, like, say, New York City, you could create a black hole that way.
I think it would have to be grapefruit size.
Great. So the size of the Earth, the size of something the size of a grapefruit. If you put that much mass in there, you'd have a very, very small black hole.
Yeah, I think if you took the mass of the Earth and made it into the size of a grapefruit,
compressed it into the size of a
compressed into the size of a grapefruit, you'd have a black hole. I think that's the order of magnitude. Yeah,
that's pretty incredible. Okay, so that's what relativity.
You'll have to check that out.
That's what relativity taught us about time dilation, right? So as you get closer and closer to the speed of light, matter cannot travel faster than the speed of light, because if you do the math, the amount of energy that it would take in order for you to accelerate that fast would exceed all the energy in the universe, and so you can't.
Yeah, so you start getting diminishing returns.
Yes,
when you're trying to accelerate,
because your mass increases.
Yeah, that's again a heuristic.
Yeah.
Don't. That's kind of like a hand wavy way of thinking of it. Just think of it as you need to increase your velocity to get closer and closer to C. You need more and more energy.
Yeah. And to the point to where it becomes impossible.
Yeah.
So you cannot accelerate matter past the speed of light. You can get it to maybe 99% the speed of light. So now here's the question I have. You are falling into a black hole, and you look out and you see one. So like now you see what? So now you're falling into a black hole, and you would go 1 times the speed of light as you cross the event horizon. Is that right?
It's not that you can enter at like whatever speed.
Yeah.
It's just that once you're past the event horizon,
you just can't leave.
No matter what speed you go at and in what direction, you're eventually going to go into the center.
Okay.
Yeah.
All right. So, but I look back, and if I am accelerating at the speed of light, once I go, because at some point going towards the singularity,
you can't accelerate at the speed of light.
Not to the speed, but almost the speed of light. I could look back and see is essentially the end of the universe, right? Because time has slowed down so much for me. I'm a static object where time is not moving, and I look back and I'm going to see infinite time.
So that there's some like philosophical discussion about this. So all this discussion assumes that like a black hole doesn't change its mass. So when you like throw something into a black hole, you're throwing in like what you call like a test particle.
Yeah.
That's like, you assume it has 0 mass, and so it's not going to affect the black hole.
Yeah.
But in fact, that's not quite true, right? Because once it crosses the event horizon, it should increase the mass of the black hole.
Yeah.
And so the event horizon should go out a bit.
Yeah.
So in fact, you don't have to travel to the event horizon. You have to travel just up to the event horizon.
And the level of acceleration.
And then you're going to be like part of the black hole.
Mm-hmm.
And then, in a sense, your event horizon shifted out. So you shouldn't fall in like an infinite time. You should fall in a finite time because the event horizon like comes out.
Yeah, but at some point I'm experiencing some high fraction of the speed of light, right?
Well, so what you would feel, right, is you'd feel this.
You'd feel dead, but obviously, yes, what you'd experience if you were in some ship of the imagination is you get to the edge, the event horizon. At some point, I'm accelerating it. I'm experiencing such a gravitational pull that time has slowed down for me that I'm looking and I'm watching the Earth just end.
Well, it's that the front end of your ship that's close to the black hole will get pulled more strongly than the back end. That's right. So you get this big shear, yes.
Yeah. Yeah, but what I'm saying is, but my time dilation would cause me to look and see the world go, the universe outside the black hole moving much faster.
That is correct, yes.
Yeah.
Well, like if I was sending you a signal, right, say I send it like every second, like as you're falling in, you'd start thinking I'm late sending my signal.
Yeah.
Because the time difference between the signals would grow.
Yeah, and it's you were watching me fall into the black hole, you would eventually watch me like stop, like not move at all.
That's correct.
Yeah.
Yeah.
Okay. Cool. All right. So
can I ask a quick question about the black hole?
Go ahead.
So, like my interpretation, of black holes is that light is constantly falling into it at a consistent rate, right, at the speed of light. And as you accelerate closer to the speed of light, you said that the beeps would decrease in speed because you're approaching the speed of light there, and then eventually it'll just stop time. You'll look behind you, and the light will still be hitting you until you reach the almost speed of light, and then everything just stops. So I don't think, if this makes any sense, like time wouldn't go backwards. It would just stop, and then you'd be skedified, and then you'd die.
It would stop for you. So here's the thing.
Yeah.
Would you die? Isn't dying like a verb? It's like a process that would have to happen that requires some form of time. There is no time for you because you're traveling at the speed of light. If you look back,
you're not falling in necessarily at the speed of light.
Okay.
Yeah, you can fall in at a different speed.
At any speed.
Yeah.
Right.
It's just that you can't leave.
You just can't leave. Yeah.
Okay. But aren't you experiencing acceleration at the speed of light?
No. So the speed of light's a velocity. It's not acceleration.
Okay.
Right. Again, just it's like a corn maze. Just that it's like Hotel California.
Okay.
Right. Whichever direction you go at whatever velocity, you're eventually going to end up.
Got it.
In the middle. It's just if you're trying to get out and I'm trying to go in, I'm going to get there first.
Yeah.
But you're going to get there eventually.
Yeah. Got it. Okay. I see. All right. Here we go. Beautiful. All right. So the disagreement. I'm trying to think of the word between quantum mechanics and relativity.
Don't think of them as like disagreements.
Okay.
Think of them as when do the theories break down?
Okay.
Right. So we're talking about Newtonian physics,
Where it breaks
right?
down.
It
Yeah.
breaks down when you start studying like length scales that are close to the de Broglie wavelength. So once you have to start thinking, oh, this isn't a particle, it's actually kind of also has wave properties. That's when you have to start worrying about quantum mechanics. You have to start worrying about relativity once you start going at close to the speed of light. So whatever that is, 1%, 10%, something like that. Now, what about quantum mechanics and relativity? So, like, what's the most famous equation?
E equals mc squared for
Exactly.
for relativity.
Exactly. So when quantum particles start being close to, start having an energy close to mc squared, where m is new particles that you can create, then you have to start taking relativity and quantum mechanics simultaneously in effect.
Yeah.
Okay. So in a sense, say you have a particle collider. If you're colliding particles at an energy close to mc squared, where m is like a new particle, then you might sometimes create that new particle. And then you have to take into account basically relativistic quantum mechanics, so quantum field theory.
Yeah.
That's when that theory comes into play.
I'm trying to understand. I understand the part like when I pull a quark away from another quark, the energy creates a new quark, but I don't understand this part. Why is there new particles being created?
So because those processes are allowed,
Okay.
in a sense. So if I just take two electrons, right, and I just like smash them together, but not at a high enough energy to be able to create new particles, then when you create new particles, two things have to be conserved: energy and momentum.
Yeah.
All right. So imagine I collide two things head on.
Yeah.
Okay. There's zero momentum in the system, right? This guy has momentum P, this guy has momentum minus P. They're going to collide.
Okay.
If they have enough energy, though, in their mc squared plus the energy from their kinetic energy, right, to create a new particle, I can, in principle, create this particle. It's going to be at rest because that conserves momentum and it conserves energy. So that will happen sometimes.
This particle is created because energy and matter are interchangeable. In this case, we have a bunch of energy coming into each other, like with energetic particles ramming into each other.
That's right.
And one of the ways of conserving that energy is to create a new piece of matter.
That's right.
Okay.
And as long as momentum and energy are conserved, it can happen.
Okay, so I understand how that makes sense with relativity.
Yep.
And how does this conflict with quantum mechanics?
So it doesn't conflict. What I'm saying is that when you reach those energy scales, then you can't just do run-of-the-mill quantum mechanics. You have to do what's called quantum field theory, where now instead of treating the quantum particles as particles, you treat them as fields, and it's actually the fields that you're quantizing, not the individual particle excitations. And
that's incredible. Okay.
This was all worked out in like the 30s.
Yeah.
Yeah, so it's run of the mill stuff now.
Yes, I'm sure the audience feels it's run of the mill. So now, where does it break down when we get inside of event horizon?
Okay, so what you're talking about is when will quantum field theory start to run into conflict with gravity?
Yeah.
So the problem with quantum field theory is you still need to have like a metric. Okay, so think of a metric as like the 4D space-time that you do physics on. At one point, you want to also take into account the quantum nature of space-time, and that description breaks down. So in a sense, it's when you have like black holes that in general relativity describe the metric. So they describe the field that you play physics on.
Yeah.
Then they also they also kind of turn into these like quantum particles that have these like quantum properties, and you want to be able to take that also into account, and that's when you start having problems.
Okay, so the math breaks down for either one of them.
That is my understanding.
Yeah.
Yeah.
It's hard for me to even understand where the math breaks down. But then when you start looking at when you start using Newtonian physics to try to describe what happens with the singularity, it doesn't work anymore because
you're far off from Newtonian physics.
Yeah, you're so far out because if you try to use Newtonian physics, you have an object that has no area.
Maybe here's a way of thinking of it. Okay, so like Newtonian physics, you assume that the playing field is just like there, like God created.
The space time that you exist in is constant.
There's no space time at this point. At this point, there's just space. So X, Y, Z, and you have a stopwatch. That's where you're doing Newtonian physics.
What was it? The Ptolemaic description of the universe that like all time would be the same everywhere, something like that. I think that's what we were talking about before relativity.
Like Ptolemy had his own version of the universe, but like Newtonian physics, just think of it as like the playing field is set. X, Y, Z, and you have a stopwatch. Then Einstein goes and says, well, actually, X, Y, Z, and time are actually the same thing. So you should be able to interchange like meter sticks and stopwatches.
Yeah.
And then kind of the problem with like quantum gravity, right, is you start to realize, there should be something quantum mechanical about this space-time.
Yeah. And
people are kind of unsure about how to deal with that.
Okay.
So in a sense, it's when does gravity become important? But simultaneously, when does quantum mechanics also become important? So like during the Big Bang, the universe is really small, but gravity is also important because that's how we describe the Big Bang. Likewise, like around a black hole, black holes can be potentially really small.
Yeah.
And yet they describe all of the space-time as well. So how do you deal with that kind of situation?
Right. Where some of these things break down. A couple of things I want to talk about the 4 fundamental forces in physics, and maybe 3, depending on who you're asking, and the idea of the theory of everything. So for those of you who are not familiar, the 4 fundamental forces in physics are the strong nuclear force, the weak nuclear force, electromagnetism, and gravity. And then the weak electro force is a combination of the two. Electroweak, sorry. The force carrying, let's see if it help me. Let me do my astronomy 101 here. The force carrying particle for the weak nuclear force is the Y and Z boson. The what?
W.
The W and Z boson. The force carrying particle for the strong nuclear force is the gluon. The force carrying particle for the gravity is the graviton, or it's a theoretical one, the graviton.
That's theoretical one.
Theoretical. And then the force carrying particle for the electromagnetic force is the photon. Is that correct? I got those right? Okay. So talking about those things, there's 2 things I want to talk about. First off, gravitons. So we talked about when Isaac Newton, he was able to describe gravity and came up with a formula for gravity based on what Johannes Kepler's observations. But what gravity was what you talked about before, spooky action at a distance. He punted. He doesn't really have a theory on what it is. And even to this day, by the way, this is one of the things that flat earthers talk about all the time, is that because we've never detected a graviton, that's the reason. Or is it gravitron or graviton? How do you say it? Graviton. Because we've never actually measured this force-carrying particle. But even though we do assume it exists, that's one of the reasons why they say, the Earth is flat. Anyway, going back to this, the graviton. How do we detect it? How do we know that it's there? What are the signs for it?
I don't think anyone knows how to detect a graviton.
Yeah.
Because gravity is so weak on any kind of scale that we probe with our particle detectors that it's really like a theoretical concept that you'd have when you say like, I collide 2 black holes together. How are they interacting?
Yeah.
We might be like exchanging gravitons, but like just to like kind of explain or the setup. Okay. So we're talking about quantum particles. They have spin. The way we break particles down is that there's spin a half particles, and those describe what matter's made up of. So you're talking about like, electrons, quarks. These are all spin one half particles. Okay. And they make up the matter. And now spin can also be an even integer. So spin 0, spin 1. okay, those are the force carrier particles.
Okay.
So the way that matter interacts, so the way that like two electrons talk to each other is they exchange force carrier particles. So you have spin half particles that exchange spin zero. So like photons or they'll like exchange them the same way that like if we're instead of like pushing each other, we like throw a bowling ball towards each other, and then that's how we interact. Okay. Now, all these particles that you talked about, except for the graviton, okay, that kind of theory is like self-consistent, right? So it's called the Standard Model, and physicists understand how to use this to explain what's happening in particle colliders. And so basically, you can use a technique called Feynman diagrams, which is basically like a little cartoon that encapsulates very complex mathematics of how these particles interact. But it's basically, you'll have like, two particles and they exchange a force carrier and then they create a new particle and then they go off on their merry way. And that represents this like complex process that has some probability of happening. Now, when you're talking about the graviton, in the sense, it's a theoretical particle because it's never been used in these like calculations at a particle collider to explain what's going to happen, because gravity is in fact such a weak force in comparison to the other three. So that's why in our like one everyday experience, and also like even the experiments that we carry out in astronomy, the description of gravity, the way that Einstein did with describing space-time as this like curved space, that's sufficient to describe gravity, and a better way of describing it than with gravitons.
Okay, got it. Well, yeah, no, with no, I understand what you're saying, right? Because we can see empirically what it does, right, and then describe backwards. Basically, it bends space-time this much.
Like in a sense, if you have one electron, right, it has some the charge of an electron on another electron is so much higher electromagnetically
than the force of gravity.
Than the force of gravity, that you can just neglect gravity.
Got it. Okay.
And so the graviton is this hypothetical spin 2 particle that, if you think, oh, we should be thinking about gravity the way that we think about the other forces, then, oh, there should be this graviton.
Yeah.
But as far as I know, I don't know how it's actually
isn't that how we also look at the Higgs boson? Like, we haven't seen a Higgs boson. We just looked at the remnants of two neutrons colliding with each other.
But again, that's part of the Standard Model. So what you're alluding to is they didn't like turn on CERN for like 6 months and then made like a jar of Higgs boson and like put it on display. Right? Because the Higgs boson has like it's like a radioactive particle. It's just going to decay. Right? And so, but they can still study the decay products, right? They can say, okay, well, if there was a Higgs boson for like an infinitesimal amount of time, what's going to come out of it?
And we can see those things.
And we can see those things.
Just like we can see the moon orbiting the Earth, and that's how we know that one of the functions of gravity, we know there's some force at a distance that's going on there.
Well, it's that, so all these particles, most of them don't live for like a long time. Right? But you can see the decay products, right? And the point is that this is a philosophical point, right? You can ask, like, how is this real?
Okay.
Right? Well, it's real because it lets you make predictions, right? About what happened, right? Like, oh, let's assume there's this particle here and it decayed into these other two particles. Does this help us predict what's going to happen in other kind of particle interactions? If the answer is yes, well then, your theory is actually useful.
Deduction. We're just using the deduction of what we've seen. Like
exactly.
Sherlock Holmes, right?
Like W and Z bosons, like they decay as well. Like don't pick on the Higgs, know. The other guys decay as well. So,
we're just seeing the byproduct of the collision, and then we know that it exists because of the byproducts.
That's right.
Yeah.
That's right.
All right, so let's go back in time. Let's talk about the history of astronomy, just some historical figures. So Johannes Kepler, who initially made these observations about orbits and different things like that. Also, the other one that I wanted to talk about was William Herschel, the first human being to ever discover a planet. So
have you been to his house?
No. What's his? Where's his house? It's in the UK, obviously.
It's in Bath.
Bath.
That's how they told me how to pronounce it when I was living in the UK. We'd just say Bath.
Bath. That's funny. So there's the idea of William Herschel. He he is the first person that he discovers Uranus. Uranus is originally called King George's planet.
What a suck up.
I know, right? To King George. And by the way, yes, this is the same King George who us Americans, whose ass we kicked back in the 17th century. The same King George that we the United States seceded from England. And then they went to Herschel and they told him, hey, we named all these other planets after Roman gods, so we need to change this up. And they named it Uranus. And to placate the most powerful empire in the world at the time, the British Empire, all of the moons of Uranus are named after what?
I have no idea.
Characters from Shakespeare's plays. Desdemona, named, there's a bunch of them. Can you look up? They're mostly from A Midsummer Night's Dream. Do you know all the planets? So they're named after Roman gods, and then their moons are named after Greek gods. So Mars is Roman. Phobos and Deimos are both Greek. Venus is Roman. And then Ganymede, Io, Callisto, and Europa are Greek names. Jupiter is Roman. So that all breaks down up until you get to Uranus. Then in that place, then William Herschel did that. Yeah. So that I always thought that was interesting how we looked at that. And then also we already talked about the formation of the moon. The solar system is always something that I find to be really interesting because, listen, I deal with some people who aren't into astronomy. But they are into astrology, and they start telling me about Mercury being in retrograde, or what phase of the moon that they're in, or the constellations, or something like that. Do you ever have an issue with this? Where
I just go with it. I'm like, yeah, I'm an astrologist.
Yeah, you say you're an astrologer.
And then I have a picture in my phone in front of like this astrology center in the UK. And just like whip that out.
Is that how it works for you? Yeah. Does it frighten you at all though? Like I do. I don't, because I'm going to insult a lot of people by saying this, and I really don't mean to. But we laugh at people who think the Earth is flat, but we don't laugh at people who don't sign contracts because Mercury's in retrograde. Do you understand what I'm saying? You kind of see where I'm going here?
Yeah,
it feels like there's a finite amount that we can understand. I mean, for people who've been watching this episode, they're probably like, holy fucking shit, this is crazy.
This is what I've realized. Like you shouldn't like judge people on their beliefs.
Yeah.
Like if I'm friends with you, right, and I know like you're a flat earther, or you don't believe in dinosaurs, or you're like astrology.
Yeah.
Like we should let's not talk about that at dinner.
That's a good point.
And let's just be friends, because I like you for other reasons. Like I'm not going to let your stupid astrology things get in the way, Like
I just know like grown adults who literally choose who they date based on their astrological sign. There was a study done in the UK where they took thousands of people, they tested them, and they tried to see which couples were more successful and they used astrological signs, and they found zero. I mean, obviously you and I would know this, zero correlation. Sorry, Libras and Sagittarius, you guys worked out just fine, just the same rate that everyone else is. But I found that was interesting. I'm actually going to have a flat earther on here. That's why I wanted to have you on first, so that I could prep myself up for some of the things that were going on. But I do just think it's crazy, like some of the level of hokum that people believe, and I do think that like you understand certain things that you and I talked about, like for instance the fundamental forces in physics or the laws of motion. The average person on the street has never heard of these things.
But it doesn't affect them.
But right, I understand that it doesn't affect them until people believe the Earth is flat. And there are millions of people who are starting to believe this now. So I think it does affect them. It affects them in that there is a void of information where they're missing something. Do you understand what I'm saying?
But just because, say, a large segment of the population believes like X is true.
Yeah.
It doesn't mean X is more true or less true, right? If average Joe on average Joe on the street believes X, right? It doesn't make X any more true. If everyone believed
the Earth is flat, it doesn't make the Earth flat.
Right. But if everyone believes the Earth is not flat, it doesn't make it any rounder.
Yeah. If you or I, listen, OJ either killed Nicole or didn't kill Nicole, and it doesn't matter what we think about it. Got it.
Yeah. And so my point is that like in lots of like issues, right, in science, this could get like spicy, super fast, right? Like in some sense, like it doesn't matter what the average person thinks, right, about these things because they're largely uninformed.
Yeah.
Right. In a way, if more people believe something, it's actually bad because it might throw like additional weight into that belief, even if it like scientifically it doesn't like it's not that strong of a claim.
Yeah, there were certain people with Einstein because he was counteracting some of the things that Newton had said, and there were people who pushed back against that.
Mm-hmm. Yeah, but okay, let's take an example like global warming.
Okay,
right. If lots of people think global warming is a problem, it's going to become an issue, regardless of whether global warming or not is actually a problem. Right? Because people are going to they're going to call their senator, call their representative, and they're going to be like, yo, what are you doing about global warming? Right? And in a sense, that's largely uncoupled from the science, right? Of whether scientists can actually measure this thing, whether scientists think that, this is going to lead to, catastrophe in the future. If lots of people believe this thing, then it will have an effect.
Yeah.
Regardless of the veracity of that claim.
Yeah.
Right. The same way that if most constituents don't think global warming is a problem, even if it is a problem, based on the scientists, it's not going to make a blip politically, and it's not going to change how people live their life.
Right. That makes sense. Yeah. But I mean, when you think about, and obviously we're a long way away from this, but 1992, the Catholic Church issues an apology to Galileo Galilei for putting him on house arrest for the rest of his life because he said that the sun was not the center of the universe. Stuff like that. I do think it's a little, I didn't think it was dangerous before. I had your belief until I started meeting rational, college-educated people who thought the fucking earth is flat. And I don't know how many, because honestly, if I thought the earth was flat, I would never approach you. I've had 4 people come and approach me and tell me the earth is flat and that we didn't land on the moon in 1969. I've had numerous people explain to me how the CIA, go ahead.
Okay, but what about when we go back to the moon? How many flat earthers you think will be won over?
None.
You don't think so? When Elon takes us to the moon?
Let me tell you something more. I'm going to tell you exactly what's going to happen. We're going to take Flat Earth Dave on it when we have cheap commercial space travel. We're going to take him up into orbit. He's going to go up into orbit. He's literally going to watch us go through the stratosphere. He's going to watch the sky get dark. He's going to see the stars. He's going to look down, and every 90 minutes, he is going to watch the Earth rotate underneath him, and he's going to come back down and tell everybody it was CGI. I guarantee you that's what he's going to do, because these people have made a religion out of this. But the thing is, they didn't use logic or reason to get into their belief system, so we can't use logic or reason to get them out of it. And that's the problem, and the number is growing. Man, I know from your standpoint, because you are surrounded by highly educated people who use the scientific method and try to disprove your own hypothesis whenever you come up with one. I am not. I live in Las Vegas.
I lived in Vegas 3 years.
Yeah, you lived here. That's right. So you know what I'm talking about.
I know all about Mercury.
Retrograde. Right. Mercury retrograde. The problem is when you have a discussion with somebody people who literally do not go see an oncologist because they think crystals will cure their mother's cancer. Stuff like that scares the shit out of me, and it seems to be growing. It seems like we are in an age where I have the ability to learn more and understand more about the scientific method, biology, mathematics, astrophysics, and yet I choose to learn less. And that is the thing that kind of frightens me.
Well, yeah, because you watch cat videos on your phone. You don't read Wikipedia.
I have 3 cats, but yes, I understand. No. But even when I watch cat videos, I'm watching something that's true. That's the problem. Right. That's the issue. It's like you saw the birds are fake. Have you seen this new thing that's come out?
But see, no, I haven't.
Yeah, it's a new thing called birds are fake. They're all like CIA robots or something like that. But it's growing. Like the part of that, it's growing. Like there are no aliens at Area 51. Sorry to tell you guys.
No, but I take a more positive spin, right? Because you're talking about all the people who have convinced themselves the world is flat.
Yeah.
Right. But think about all the people who have educated themselves through the internet. Mm-hmm. Those people 100 years ago wouldn't have been able to educate themselves because they wouldn't have access to a massive library or basically all of human knowledge at their fingertips.
Incredible, yeah.
And so you're thinking why are there X percentage of people that are choosing to stay uneducated? But I take a more positive view. Look at all the people who have access to all this knowledge.
Yeah.
Right. So
I hope you're right and it stays that way. But I have absolutely run across people who, again, man, we had a guy on here, we had the autism, vaccine debate, and it just the level of hell that I caught after we had a guy come on in here, or the thing about COVID, vaccines and COVID. And the level of hell that I caught from people, because they didn't want to believe something that we could prove through peer-reviewed science, it just really, really got ugly very fast. And I agree with you to a certain point until they put me on house arrest because I said that the sun is not the center of the universe. Then I don't agree with you anymore. Do you understand what I'm saying? And I know it seems like we're far from that point, and then sometimes I don't think we are. Sometimes I'm very confused about that situation. I literally I went on a Tinder date once, and a girl literally got up and left because I told her I was vaccinated. That is, I understand these are not isolated events. This is a frequent thing that I notice.
I tried to get some colleagues on your show, and they didn't want to go because they thought you're going to debate a flat earther.
No, I am going to debate a flat earther.
They thought they were going to debate a flat earther.
I'll handle it. Trust me. I got got this one, especially with all the information I got from you. You understand they don't believe in gravity, right? They believe in density. They believe that objects fall to the ground because of air. It's in madness. If you ever want to go over it, I basically took some time and watched a bunch of their theories because I look at flat Earth like I look at Game of Thrones, right? There's a ice wall and the dragons can fly here and do this, and there's certain rules, and you can't conquer Dorne and all this weird shit. I take those rules, and like also the Silmarillion, which is in Lord of the Rings. I took it and I looked at flat Earth like that. I was like, okay, explain to me your fucking rules, because I'm trying to learn them. Because now that I learn them, I can have a debate with you. And I've had several people tell me, why are you doing this? This is stupid. But I don't think it's stupid. I want to hear what somebody has to say who is saying, complete craziness. And I want to be able to try to understand where he's coming from, and then be able to have an intellectual debate.
We get crank emails all the time at work.
Okay.
So like that's kind of like a metric of how like famous you are as like a physicist.
Yeah.
Like super famous people, they get like actual people come up to their office door and tell them, "Oh, I want to tell you about my theory of the universe."
Yeah.
Versus like I just get like the occasional email, of like some guy that created this theory. Right. Some of them are actually quite wealthy.
Yeah.
Because they're like retired engineers and stuff. Yeah. And they apply their little like engineering theory to like try and understand like the entire universe.
Yes.
And they produce these massive books, like hundreds of pages, color illustrated. And they spend, thousands of hours on this and lots of money. And then they mail it to you for free.
That's incredible.
Yeah.
That is absolutely incredible.
I should send you one of those books.
No, I would like it very much. I have a bunch of flat Earth studying to do first. But yeah, no, just going back through like the history of astronomy, like the things that we didn't know, and then all of a sudden we did know, or the unbelievable ability for instance, when Galileo first sees the moons of Jupiter, right? We call them still to this day the Galilean moons. When he sees that, and now he comes to this realization. Just imagine like the strength it took him. He comes to the realization. He's like, wait a second, those are moons. We have a moon. Oh, wow. What does that mean? That means that, not only these other planets right there, they're just like us. That means we're on a planet. That means this is a planet. That means that we're orbiting around that sun. That sun is 93 million miles away. And I got to go tell the Pope this, and now I'll go get locked up for it.
Yeah, but Galileo just got locked up. There was another guy who, I forgot his name.
He's a monk. I know you're talking about his monk. Oh, my goodness.
They like killed him.
What was his, where did he live? What was it?
Probably Italian. I don't know.
Oh, gosh. I wish I could, because I remember... Neil deGrasse Tyson talking about this monk, and I remembered his name before, but I forgot it. But I know exactly what you're talking about. Yeah, they did kill him. They killed him because of his beliefs, just like what Galileo had.
Yeah, he realized that there were other planets and maybe there's life on them.
Yeah. Oh yeah, there would be other life, and of course that goes against something in the Bible, because I remember I used to be part of a Christian ministry, and the explanation I was given by this Christian ministry is that there cannot be aliens, because those aliens could never have heard of the redeeming power of Jesus Christ.
You see, I hate that philosophy. We should go tell them about.
Yeah, exactly. We should get out there and go do it. Okay, let's lead to the next thing, okay? Because this is because people know that I talk about astronomy a lot. The number one question, we'll go over the number one questions you get. Obviously, the number one for me is, are there aliens? Have they visited us? And the thing that I say, and you can correct me if I'm wrong about this, Proxima Centauri is 4.1 light years away. That's a little bit more than 24 trillion miles away from us at the speed of light. It would take 4.1 years. We can't even go 1% the speed of light. So even if what is the fastest we could get, like Voyager, with a gravitational assist from Jupiter, like 75,000 miles an hour or something like that?
So I think realistically we could probably hit like 10% of C if we had like fusion rockets.
Okay, fusion rocket, but with gravitational assist today in 2021 using Jupiter, we're not even 100,000 miles an hour.
I have the number 21, but I don't know the units.
Yeah. Okay. Well, not even 1% C. Right.
I want to say like 21 kilometers per second.
Something like it takes something like 175,000 years for us to get at that speed to get to Proxima Centauri.
Which just means we need better rockets.
Oh no, I agree with you on that. What I'm saying is, these better rockets, now you think we can get 10% C? So it's 40. So now it's 41 years.
So what's the basic physics of a rocket?
Yeah, you have to leave something behind.
Yeah, you have to leave something behind, right? And so what basically sets your velocity? So the basic physics is that, imagine you have like a sled, and you have like snowballs, and you're chucking snowballs out the back to propel your sled forward. Yeah. The first snowball that you chuck out is not going to be very effective at accelerating you, because that has to accelerate you and all the snowballs that you're carrying to chuck out at a later time. Okay, and so what basically limits you is the exit velocity. It's how fast you're throwing the snowballs out the backside. And basically right now with chemical propulsion, you're basically limited to going like, a few times kilometers per second.
Yeah.
Okay. That's very limiting in the sense that, okay, we can get to like Mars in 6 months and maybe Jupiter in a few years. And, Voyager's been going like 40 years at this point, and we barely left the solar system.
Yeah.
But imagine we could have like fusion rockets. So a fusion reactor.
What's it leaving? Now I've heard this idea of fusion rockets or ion propulsion. What is according to Newtonian physics? What is the thing we're leaving behind with the fusion rocket?
So something I was reading about recently was like a nuclear saltwater rocket.
Okay.
Okay. So imagine. I was like, do you know roughly how a nuclear reactor works?
I do actually.
Okay. So for the viewers at home, you basically have particles that are radioactive, and they produce neutrons.
Yeah.
And those neutrons are used to hit the nuclear particles.
Yes.
And those will release more neutrons.
Yeah.
And so you get this like chain reaction.
Correct.
And
Same thing in a nuclear bomb. You have one part that detonates the other part. Correct.
That's right.
Yeah.
And so what you do to control this kind of situation is you have some kind of chemical. So for usually I think it's like boron control rods that you use to basically absorb the neutrons so that you have precisely the right amount so that the number of nuclear reactions you're having isn't growing, but it's not decreasing.
So
then you can have constant power.
Constant power,
Okay.
which is when Chernobyl, it was the boron rods that did not go down in time, which has caused the nuclear reaction.
And then it goes out of control.
And it goes out of control. Yep.
Okay, so imagine a kind of a rocket where you have a sustained like nuclear reaction in the like hull, and then as soon as they exit the nozzle, then they go critical.
Okay.
And so then you basically have this like nuclear bomb going off as it leaves the nozzle.
So this is now I understand. So this is the function for those of you who watch The Expanse, which I would recommend again. The Epstein drive. That's exactly what they do. They have nuclear pellets, and they use that in order to propel themselves all the way out to Neptune.
So roughly, if you have like a good rocket,
Yeah.
you can go roughly 2 times the exit velocity. And so the exit velocity.
Exit velocity of Earth. So 11.
No, the exit velocity of the particles that
Okay.
come out the other side. And so with this kind of design, like a nuclear saltwater reactor, you could probably go like 10% of C.
That's incredible.
Which
Okay.
like 10% of C, that would give us access to pretty much the whole solar system.
Pretty easy, yeah.
And like some crazy people could go to Alpha Centauri.
Well, their grandchildren could go to Alpha Centauri.
Well,
Or their kids.
Well, if you're going 10% of C, you get there in like 40 years.
Yeah.
So you
And
start
you're actually
start when you're 20, you
it's
get there
not,
when you're
but
60.
it's not 40 years though, because you're going 10% of C.
Yes, so it takes four
But
years.
you're not going to age 40 years because you're going 10% of C.
Yeah, but the time dilation at 10% of the speed of light's not so big.
Is it? But is it even 1%? Because I know the equation I heard is at 86% the speed of light, your time dilation is 1/2.
It's highly nonlinear though.
Okay, I know.
Yeah.
I know it's not linear, but
Yeah.
but there is some time dilation, right?
Yeah, but it might be like a year or something.
Okay,
but
yeah.
like it's
There
not,
you go. 40 years. So instead of aging 41 years, you average age 40 years.
Yes,
Got it.
yes. So I feel this kind of like technology is just like it. Like you can write it down. You can like kind of like design it. So it's not like completely like science fiction.
Mm-hmm.
If you go and you say like, oh, we're gonna create like a whole bunch of like antimatter, like an antimatter rocket, and
Yeah.
then we're gonna collide the antimatter
That's
and
a
make
problem.
equals mc squared material. Like we can't make antimatter with any kind of like frequency. you
Okay.
know? The amount that we produce is incredibly tiny. We don't know how to store it. But something like this, like that I just kind of fleshed out, like that's like in a sense reasonable.
Okay, now
You know?
it's reasonable to take 40 years to go to Proxima Centauri, which most likely has no life on it or anywhere near it.
Well, we're gonna bring life.
Okay, I understand we're going to bring life, but let's go back to the original question was about aliens.
Yeah,
And why
yeah.
I personally don't think they have visited us because Proxima Centauri is the closest, that's why we call it Proxima. It is the closest star to it's a binary system, isn't it? Proxima A and Proxima B, right?
I think there's a C too.
Oh, there is okay. So that's the closest star. Most likely there is no life there. And the other stars are orders of magnitude further away. I'm not saying there certainly is life somewhere else. Would you agree? The Fermi paradox would would lean towards that conclusion. I just don't think it's basically, you have a neighbor in Siberia. What's the likelihood of you guys bumping into each other walking your dog? That's essentially what it's like, what I think with alien life.
So, okay, I literally just came up with this argument right now.
Okay.
So if we're rare,
Okay.
wouldn't aliens want to come visit us?
Right. But aliens who can travel at a high percentage of C are way fucking more rare than we are. That's the point. I just don't think we're that interesting.
Yeah, but okay, so then the alternative, if we're not that interesting, means there's a lot of us around.
No, I agree. No.
And so there's either a lot of like species at our level,
Yeah.
or we're actually really rare.
Or there could have been a lot of species at our level, and during different protostars and different proto-solar systems, they had a species that existed. I personally don't think we're going to make it a million years. There's too many ways for us to die.
But the point is that we don't have to make it a million years, right? Like we basically, like you said,
we have to coincide with another species in order to bump into them. If they let's just say there is realistically another, in a galaxy far, far away a long time ago, there is another species. At some point, in order for us to coincide with each other, even if they send their beam and it gets to us, if we're still in the 1850s, we're never going to receive that beam.
But you see, you're assuming that we like communicate in like conventional ways, right?
I mean,
like,
we better communicate in some kind of way. I mean,
because maybe imagine if the way we communicate is actually by like spreading life.
Okay.
Right.
Right.
And so
we're going to get to that also. We're going to talk about panspermia.
Yeah.
at the end.
So
go ahead.
So in that sense, right, if we just try and like spread light,
Mm-hmm.
right, then in a sense we've been like successfully communicated to if panspermia was how we, came to have life on Earth.
What was
right?
the contact? You remember we were receiving?
I told you I don't watch movies.
Oh my
I don't
God!
watch-
You! Oh my God! A theoretical physicist who has not watched the movie Contact. Get the fuck out of here! They basically receive a message from Andromeda, and and it gives them instructions on how to build a machine that would allow them to enter a wormhole. And in doing so, that they're now
is that the one with Arnold Schwarzenegger?
negative. It is with Jodie
Jodie
Foster
Foster.
and
Yeah.
Matthew McConaughey.
Okay,
That's
I have heard of this one.
Okay, yeah, it's pretty good, and it was written by who's the guy, the original Cosmos? Well, I can't remember his name.
Carl Sagan.
Carl Sagan wrote a novel called Contact.
Yeah,
and
yeah,
Jodie
yeah.
Foster and Matthew McConaughey. Really good, really cool concept. Very weird ending, but it's. I definitely think it's definitely
Don't
worth
ruin
watching.
it.
No, I'm not going to ruin it for you. But just the idea of man, I got so many science fiction things for you to read, and you're a theoretical physicist. You don't read any of them. It's crazy. So just the idea of we'll go back to aliens. The likelihood that they ever, back to the astrology thing. It's the ancient aliens. We've lost the technology to build the pyramids. I'm sure you've heard this a million times. All this kind of stuff. It's like normal physics or normal evolution or normal anthropology is not good enough for people. It's got to be fucking aliens that came here and did this stuff. And I'm just like, if these aliens are made of matter, well, I'm not going to assume they're made of carbon, but they probably are. If these aliens are made of matter, then the incredible distances that they would have to travel to come to see us without even knowing that we exist, that to me, I have a very difficult time believing that has ever happened, which is why I don't think there was an alien spaceship in Roswell, New Mexico in 1947, and I don't think Megatron is in the fucking Hoover Dam either. Like, I don't think that's real.
I've never even heard that one.
Oh my God, dude, this is crazy, man. This dude has never seen Transformers.
No, I've heard of Transformers.
Yeah.
I didn't know that was the plot.
Yeah, one of the plots, Megatron is in the Hoover Dam. But like that kind of stuff, I find it to be wild. I'm just curious. I'm just going to let you go on. What do you think about the prospect of aliens having been here previously, even before human existence? Prometheus, another movie I'm sure you haven't seen. The aliens currently here now, aliens coming here in the future, or us eventually coming into physical contact with another civilization.
So I won't. So I'll put money that we'll probably discover life on Mars.
Okay.
Not like
microbial life underground
life.
that probably was there at some point.
Yeah, I'll put money on that.
Okay.
I think there's probably aliens somewhere in the galaxy because I don't think I'm that special.
No,
I don't think we're that special.
Again, no, absolutely agree with you.
And I think so. Going back to like JWST,
Yeah.
I think we have like solid prospects in
James Webb Telescope.
James Webb Space Telescope.
Yeah.
I think we have like solid prospects to start answering questions like, is there advanced civilization in the galaxy? So like, I was telling you about how JWST can measure the gases in exoplanetary atmospheres.
Yes.
So we can do like different kinds of tests.
So we're looking for the nitrogen and the oxygen mix and the Goldilocks zone and all that kind of stuff.
Well, I mean, the Goldilocks zone we can kind of figure from looking at the star. Like how hot's the star? How far is the planet from the star?
Yes.
Okay. From looking at those gases, one
other thing before you go on,
Yeah.
Kip Thorne and the idea of Gargantua, the black hole that had hydrogen clouds around it that was able to produce light for orbiting planets. Would that actually be something that was feasible?
I've never heard about that.
You have never seen the movie Interstellar.
No, I've met Kip Thorne, but I've never.
Are you kidding?
No.
This is
No.
crazy to me. So but for those of you who don't know, the guy who did the science for the movie Interstellar, my favorite movie of all time, he also won the Nobel Prize for the what was it? Was it the gravitational wave?
Yeah,
thing?
gravitational for LIGO.
Yeah, so he wrote a book called the Science of Interstellar. Someday you will watch that movie. He wrote a book called The Science of Interstellar, and then after that he won the Nobel Prize. So now going back to what we were saying before, the prospect of aliens. Completely agree with you. There are other life forms in the galaxy.
So once we start measuring what gases are in those planets or planetary atmospheres, one thing we can look for is technosignatures. So we can look for gases that wouldn't be produced naturally. So mostly like CFCs, so chlorofluorocarbons.
Chlorofluorocarbons.
The things you put in fridges, so
Yes.
they work. Okay, those things can't be made in nature. Okay,
There has to be life, like
you
breathing it
need
in,
some kind of like
pushing it out.
Yeah, exactly. Yeah. We can start looking for that. Also, would be a great way to like terraform a planet, right? Because they were like incredibly powerful greenhouse gases.
Sure.
And so, if say you have a planet, it's a little too cold, you put a bunch of CFCs up in 100 years, it heats up. Now you can live there. That'll be one example, right? The other example we can look for is, so imagine we look at a certain patch of the galaxy and there's hardly any planets that have oxygen. But we notice this like one region that has a whole bunch of planets, all with like high degrees of oxygen. Well, that might be evidence that there's actually an alien civilization that's terraforming those planets, making them more habitable for their species.
Would we be able to see a Dyson sphere if we had that James Webb Telescope?
Oh, that's a good question. I don't know. I don't know exactly what a Dyson sphere would look like.
It would look like nothing. It would look like you would see basically solar panels surrounding a sun and absorbing almost 100% of the sun's energy, using that energy to fuel an interstellar species.
Like, I don't know how effective a Dyson sphere would actually be, because you probably wouldn't want to build it like around the whole star, right?
Maybe. I mean, it depends on how much energy you can get on the planet. You might not need the sun. Who knows? Who knows how these people would work?
I'm look, all respect to like Elon Musk. Like,
Yeah.
I'm not the biggest advocate of solar power.
Yeah.
Yeah, I'm like nuclear all the way.
It's not super efficient, right, compared to how nuclear power works, for sure.
I mean, even just imagine like putting up solar panels
Yeah.
like in space. Like, why not just build a nuclear reactor?
Yeah.
Like 1% of the Earth is like thorium. It's like
Yeah.
it's not like we're short on nuclear fuel. And then when we run out of like thorium, we can go to like Saturn and harvest the helium-3 and do fusion.
Okay, isn't there helium-3 on the moon?
Yeah, not that much.
Okay.
Like, okay, if you compare the moon to like Saturn's like the Middle East for oil.
Yeah.
Like, we can just like harvest helium-3.
From where? From Titan?
No, Saturn.
How are we going to harvest it from a planet that has no surface? I'm confused.
Well, you just fly in, you just like fill up gas and then just leave.
The helium-3 is just floating around?
Yeah. So there's two kinds of helium-3 and helium-4.
Okay.
Helium-4 is like the normal kind.
Yeah.
Helium-3 is the special kind that you can use to do fusion fairly easily.
Wait, is there... Okay, now I remember what you're saying. Okay.
Yeah.
Okay, makes sense. And then O2, and then O3 is ozone. And then the sun particles...
So O3 is what we want to look for in the exoplanets.
Correct.
Because it's much easier to detect than O2.
Yes.
But it's a sign that there's O2 there.
Okay. Got it. Okay, because and then for our ozone layer we have O3, which is ozone.
So
then the light part or the photons or the what is it that hits the atmosphere and then breaks up the O3 into O2 particles?
But I think it's just some like UV.
Yeah, just UV radiation.
Yeah.
UV radiation, the energy from UV radiation breaks up the O3 into O2.
But the point is that O3 is a stronger signal in protoplanetary atmospheres.
Okay.
And so if we want to try and measure, is there oxygen on this planet? We look for O3.
Okay.
Yeah.
That makes sense.
Yeah.
So we'd be able to see that with the James Webb Space Telescope.
That's right.
Right.
Like, and that's probably like I think the most exciting thing.
I agree with you about it being exciting. I still don't think aliens are going to come hang out with us.
No, but then it goes next level.
Okay.
Right? So have you heard of the solar gravitational lens?
Negative.
Okay. So
Oh wait, yes, yeah, okay, yes, I do.
yes. So the solar gravitational lens is to basically use our sun as a gravitational lens to be able to image exoplanets. Okay.
And that would work better than the James Webb Telescope.
So at James Webb is you're just going to be doing spectroscopy with the
Wait,
planets.
so there's no visible light?
Okay, you're not going to like see the exoplanet and you'll be like, oh, there's Africa, there's North America. Like it's not going to be that kind
No,
of
I understand that, but
resolution, right?
are there any? So, do you remember the original? Whenever they sent out Voyager the first time, there was an argument about whether or not they should have any color pictures whatsoever that were able to come back, and they said, of course, man, we want.
I'm not that old.
Oh, sorry. We want, back in '77 when they did this. Originally, Carl Sagan argued, it's like, no, we have to have some sort of photography that comes back to Earth. This can't just be spectroscopy and radio waves. We need to see how beautiful Saturn is, because that's where we get our funding for NASA.
Yeah.
Right? Saturn's probably the most beautiful object in our solar system. Right now, when we go do the same thing with James Webb, are you telling me that James Webb can't take pictures of stars?
You know what? I'm not sure.
Okay.
You should ask
That would be very sad, because some of the most beautiful pictures you've ever seen in your life are from the Hubble.
There will be beautiful pictures. I'm saying the pictures of the exoplanets won't be
of course, you're not going to see the elephants running on
You won't see
the,
like a pale blue dot.
Yeah.
Okay, of like the exoplanet over.
Yeah.
Right. But I'm saying with this like next generation, like with the solar gravitational lens, you actually could have that resolution. Like you're talking like 100-meter resolution of an exoplanet.
That's incredible.
That's like way off, like 100 light years away. And like that's incredible, because at that point you'll even be able to figure out like what the weather's like.
That's incredible. That's actually one of the parts of Mass Effect 3, which is a video game, which I'm sure you have not played. But that's how they actually fly to Andromeda, and on their way to Andromeda, the way they are able to use it is solar gravitational lensing, and able to see what's going on in Andromeda. It's pretty crazy. All right, interesting. So back to the whole thing with aliens. You kind of agree with me though. They're not here. Do you think they're here?
I mean, I haven't met any.
Okay. All right. He's not going to give me the answer. All right. I'm looking for it. Excellent. Theory of everything. The idea of us having one one equation that explains all four forces of all four fundamental forces in physics. Do you think that's a thing to pursue?
Well, so I think, okay. So going back to this idea of like quantum field theory. Okay, I think one of the most interesting things that came out from that theory is this idea of like, what is an effective field theory? Okay, and that's just a fancy way of saying that every physics theory is going to have some special or some domain where the physics breaks down. And understanding where that physics breaks down is key to understanding the limits of your theory. And it seems reasonable to me to think that one can actually write down a theory that will like hold to arbitrary energy scales.
Yeah.
And so I think it's not a waste of time. I think it's definitely a worthwhile endeavor.
So in this case, since we have discovered how the electroweak theory, so electromagnetism and the weak nuclear force, we understand how they're connected. There would be a way that the weak nuclear force would be connected to the strong nuclear force, and the electromagnetic force be connected to gravity. You think that that's a noble pursuit, or even if that's something even real?
So what? Well, I think it's definitely like a worthwhile endeavor.
Yeah.
What's unclear at this point? So the way that people have tried so far is to use the same language to understand gravity as to understand the other three forces.
Yeah.
Right. So they said, okay, there's a force carrier called the graviton, just like the other forces have force carriers, and you can understand this physics using quantum field theory. And the idea is that, okay, well, maybe you need like a new kind of description to be able to explain that kind of physics. The same way that you can't, even if you like wanted to understand like tiny particles using Newtonian physics, you wouldn't be able to, right? You need like a fundamentally new language to write down quantum mechanics, because it has fundamentally different properties.
Okay, got it.
And so this kind of like new theory that explains both gravity and the other three forces, maybe you need like an entirely new language.
Okay.
And so that's kind of, I think, the takeaway from the last like 40 years, or maybe 1980s to 2000, is, okay, we need like a new language You can't just do quantum field theory to explain gravity.
So I know one of the explanations I've heard, again theoretical, about the idea with quantum mechanics is that these are multiple. Like when I go look at this object and it collapses, there's a universe that has a reality that has split off where the charge was up, and then the reality that I'm in where the charge was down. And every time we do this, we're splitting into different realities. You don't believe in that?
Yeah. So I think what you're talking about is the many worlds hypothesis.
Yes.
So I think that's just a way of thinking about quantum mechanics, which I think is not. I'm a very utilitarian person.
Yeah.
Like I kind of only think about things that are useful to me.
Yeah.
And so a theory like that isn't like terribly useful. Like it doesn't help me like
the Schwarzschild diameter is useful to me. No, I'm joking with you. Yeah.
Like it doesn't help me like understand things.
Yeah.
Right.
Useful to you as a theoretical physicist, of course.
Have you heard of like brain world cosmologies?
No.
So this is this idea that we live on a brain. So think of it like a membrane.
Okay.
A brain is short for membrane.
Yeah.
Okay. And so the idea is we live on one membrane, and there's another membrane kind of like further off. And
you talking about the quantum foam that professor?
No. So the idea is that we live on this one brain, and gravity happens to be weak here, but on this other brain, gravity is actually strong, just as strong as the other forces.
Different universes with different fundamental forces.
It's like, so have you read any books by Lisa Randall?
Negative.
So she's a famous physicist at Harvard.
Okay.
She's written a couple of books, and this is one of the things she worked on.
Interesting. Well, yeah, I mean, there'd be other universes where, like, for instance, if we didn't have the forces the way they are now, we would never have electrons combined with neutrons.
But the thing I want to emphasize is, like, this, it's not just like some dude, like, drawing a cartoon. Like, oh, imagine there's, like, one brain here and one brain there. It's like those brains are actually, like, solutions to Einstein's equations.
Okay.
And so it's actually consistent with Einstein. Okay. And then it's just saying, okay, well, we live on this one brain. There's this other brain where it's not, where gravity is actually strong. And so it's like a lot of theoretical physics goes from having like an intuition about how the world probably should be based on like symmetries. And so when like theoretical physicists see things like, oh, gravity's weak, the first question is like, well, why? Mm-hmm. Why is it weak? And
I still don't want to know why it goes the speed of light, but yes.
I mean, I think that's a great like fundamental question. Like I take like very like positive.
But the thing about the theory of everything, this is something, whatever the graviton is, it's moving at 300,000 kilometers per second. And whatever the photon is, guess what speed it's also moving at?
So the speed of light actually falls out from electromagnetism.
Yeah.
So you can write down like what's the physics of electrical charges, and then you can write down what's the physics of magnetic fields. And it turns out that you can actually combine those equations in a consistent way.
Yeah.
And if you do so, then electromagnetic waves just kind of like falls out. And those electromagnetic waves have a speed, and it's set by, basically two constants, like the permeability of space. And so in a sense, if you just write down electromagnetism, the speed of light being constant just falls out.
Okay. What do you mean falls out?
Like you don't actually say like let there be a speed of light. Mm-hmm. You just write down electromagnetism, and because it's a relativistic theory, you're gonna get
ergo there is a speed of light.
Ergo there is a speed of light. Yeah, it didn't have to be like postulated.
Another question I've had: quantum tunneling and the strong nuclear force. Do they have anything to do with each other? So just for those who don't understand, you guys remember from your elementary school magnet class, your science class, where they took two positive poles of a magnet and they pushed them together and they repelled each other. And then you put the positive side to the negative side and then they stuck together. Neutrons have a neutral charge. Protons have a positive charge. Electrons have a negative charge. In the nucleus of some atoms, there are protons next to other protons. In order to do that, there must be some force that causes them to come to each other. That's where we come up with the idea of the strong nuclear force. So what is that, and how does that work? And then there's an idea of quantum tunneling where it goes through that charge, and then now all of a sudden the two protons are touching each other. How does that work?
So a proton is not actually a fundamental particle.
Okay.
It's made up of
quarks.
Quarks.
Yeah.
And those quarks have to be bound together. Like I can't just give you a quark.
Right. If you pull,
like if I give you
the energy it takes me to pull one quark away from the other two quarks creates a new quark.
Yeah. The way, just think of it like they're attached by springs.
Okay.
Okay. And as I pull them away,
The harder
the spring pulls back harder and harder. So you can't really like separate them. So they always come in like pairs. So these are 2 or 3.
3.
Okay. Well, some particles have 2.
Oh, really? So there are quarks that have.
Yeah.
There are particles that have 2 quarks.
Yeah,
Okay.
they're called mesons.
Okay.
So they'll have like an up quark and a up and an anti-up.
Okay.
Something like that. Okay. Because like the charge always has to be like an integer number, and quarks have fractional charges.
Okay.
So you either have like a quark and its anti-quark, and those are called like mesons.
So, but they would cancel each other out and be like a neutral charge,
Yes,
or
something
when you
like
so
that.
you'd have a third, and a third, a positive charge for a proton.
Yeah.
Okay.
Yeah. Okay.
This is the particle physics part of the podcast that you guys were waiting for.
Yeah,
Go ahead.
Yeah. What were we talking?
So we were talking about glue. So my question was about gluons, strong nuclear force, and quantum tunneling.
Okay, so one of the like earliest ways of explaining radioactivity, okay, was through this like tunneling idea. So you imagine like the nucleus of an atom is just this bag of like protons and neutrons.
Yes.
And then if the nucleus decays, it means it like shoots like basically like a helium atom.
Okay.
So it basically like loses
A helium atom. So helium. So one neutron comes out with an electron.
Two protons, two neutrons.
I'm sorry,
just
helium.
like-
I keep thinking hydrogen. So
Yeah.
I'm sorry, brother. You're right. Okay, go ahead.
It just like comes
I keep
out.
saying
Okay?
I keep saying helium, and I'm thinking hydrogen.
So the way they like modeled this is they said, okay, just here's this bag of protons, and what's the chance? And there's like a potential well. So there's basically like a wall that this like helium atom has to like come out of.
Uh-huh.
And so the way they modeled this was through quantum mechanics. You can have like tunneling.
Yeah.
Right. So the idea of tunneling. So classically, let's think about it in terms of like money. Right. So you're in this jail, right? And to leave the jail, you have to bribe the jailer like $100. Okay. So classically, if you have less than $100, there's no way that you can leave the jail because you don't have enough to bribe him. But quantum mechanically, the way to like think of it is that sometimes even if you don't have enough energy, you can still overcome that amount. So even if you don't have $100, sometimes you'll still be able to slip through.
Yeah.
And that's this idea of quantum tunneling. So the way they modeled radioactive decay was they said, okay, there's this potential. So there's this jailer I have to bribe. The particles don't have enough to overcome it, but sometimes they'll still get through. What's the probability it gets through? And that's going to tell us how likely it is for that particle to decay.
Okay,
I think that's where that comes from.
But what is the function that's causing the particle to get out? I still don't understand.
So
is this the superposition of the particle? It could be out.
No.
Be
So
in?
so it's this. Well, it's this idea that you can tunnel across a barrier, right? So in quantum mechanics, the way you describe particles is a wave function.
Yes.
Okay. So think of, we're in Vegas, right? So wave function is kind of, if you take the wave function, it's just a mathematical object, okay?
Yes.
But if you square the wave function, it tells you what's the probability that the particle is at that position.
Okay.
Okay. If I write down what's the wave function of my particle, some of that wave function will leak out past the barrier. Okay, so in a sense, it's not.
So that's why I said superposition.
It's nonsensical. It doesn't make sense
From a Newtonian standpoint, it makes no sense. But you're talking
from
about
a quantum mechanical point of view.
Doesn't make sense.
It makes no sense to write down. Okay, the whole particle is in this room.
Yes.
There's going to be some fraction of the particle that's outside the room.
Oh, okay.
And so sometimes when you ask the particle, "Where are you?" He's going to be like, "I'm outside the room."
And that's how electromagnetic decay happens. This is a theory
radioactive decay.
That's
how one way of that they modeled radioactive decay.
Have they proven this? Is this just a theory, or
it's just a way of like calculating these things.
Okay,
right? You say, okay, my particle is like a particle in a box. How high are the walls of the box? And then what's the probability of being outside the box?
What's the probability of my cat being dead or alive?
Yes. That's how they modeled the decay.
Okay, got it. All right, so that's tunneling. Now, the strong nuclear force. How do I take two protons with the same positive charge and put them together with the strong nuclear force? What's going on there?
Okay, see, what you're asking is like, how do I even have this bag of protons?
Yes.
Shouldn't they repel?
Yes.
That's part of, all these gluons are interacting with each other.
Is this just deduction? Is like we just see the protons next to each other and said, "Fuck it, that's a force. It's got to be."
So the theory is predictive. So you can like write down, okay, what happens if I have this like bag of quarks and they're interacting with like gluons. But yeah, like it's definitely like incredibly complicated.
It is
yes.
Okay.
Like people, they do these like heavy ion collision experiments. So the one experiment, I don't know if it's still running. It's called RHIC, the Relativistic Heavy Ion Collider. It spells Rick apparently.
Yeah.
RHIC.
Yes.
And they just take these like heavy atoms. I think they take like lead atoms or something, and they like smash them together and they see what comes out.
Okay.
And so that's how they study the strong.
Wait, so
nuclear force.
protons actually do stick to each other when they do that?
They, like the quarks and gluons interact, and you see what comes out.
Okay.
Yeah.
Got it. Okay, so now the specialty, right? I mean, the first time I'm exposed to the theoretical physicist is, or most people, is Sheldon Cooper on Big Bang Theory, which I'm sure you've never watched also.
I'm familiar with Sheldon.
Yeah, so Sheldon is the theoretical physicist. Leonard Hofstadter is the experimental physicist, and then Koothrappali is the astronomer, and then the other guy, God, what's his name? Do you know what I'm talking about? You ever watch Big Bang Theory, Travis?
No.
The other guy's an engineer, but he only has a master's degree. So Sheldon Cooper always makes fun of him for only having a master's degree.
When I meet people, I just say I'm like Sheldon.
You're like Sheldon.
I'm like shy of girls.
We'll fix that also. You're going to be famous after this. All right. So theoretical physics. So here's the thing I like to explain to people. For a living, I work for a prop firm where I trade stock options. So stock options are a derivative of options, right? And
you got me into options trading.
Did I? That was the reason you got me.
Thanks a lot.
Okay. Well, so I got into it, and one of the funny things is if you look at Charlie Munger, who is a huge, he is a huge guy in finance. His background is actually physics. If you look at, is it Fisher Black? I believe his background is mathematics, and also physics. And then there's one other guy, I'm trying to remember who it is, another guy who's in, Jim Simons. He hires a bunch of physics PhDs to work because of financial modeling. He hires a bunch of physics PhDs.
He also donated a bunch of money to found a physics institute.
There you go.
Well,
okay.
they do all kinds of like computational astrophysics.
Isn't it crazy that is funny, because one of the things that I found is that so accounting is finance going backwards, where it's almost like anthropology for finance, right? We're going back in forensic accounting. We're going back and seeing what used to happen, right? When we look at physics is modeling. Finance is supposed to be modeling for money, but it isn't, because nobody in finance is able to predict anything. Like I'm telling you right now, any of you guys who bought some kind of fucking Bitcoin product, they don't know shit. They don't know whether or not the market's going to go up or down. But the funny thing about physics is you guys can model. This is one thing I like to tell flat earthers. When the newspaper says there's going to be an eclipse tomorrow, they're right 100% of the time. In fact, I'll bet you there's a high degree of certainty you could come up with every eclipse that's going to happen for the next million years between the sun and the moon and the earth, and with that that's the thing, we're able to model out into the future. So I've seen, like you mentioned before, Jim Simons tends to hire a lot of physics PhDs. In fact, I've heard there are a good number of physics PhDs that work in finance. Have you heard this also?
I mean, a lot of friends, they went to Goldman or.
That's crazy to me. So that is true. These guys are physics PhDs and went and did that. Theoretical physicist, astrophysicist, or is there some specialty?
Anyone who's good with a computer.
Wow. So computer modeling, because you are trying to, because essentially
you just have to be able to code, basically.
Well, but in physics, you're trying to create, like you said before, a testable theory, which should be able to predict the future to some extent, to some probabilistic extent.
Well, a lot of these like hedge funds, they're trying to like limit risk.
Yeah.
So you're basically like writing down what's the solution that will let me like limit my risk. So like hedge my risk.
Yeah.
And so it's just basically like computer modeling.
That's holy shit, dude. I didn't even know it was that like that. That's crazy.
But the thing is like modeling's a good thing, but your models are only so good, right? Like it's this like Nassim Taleb idea, right, of like black swan events.
Yeah, well, you also have to deal with Brownian motion, no matter what model you come up with.
Not only Brownian motion, but also like things that haven't been put into your model, right? So like if you don't put a certain effect into your model, there's no way that you're going to like predict that effect.
You do not know about the conversation that Warren Buffett is having with Elon Musk right now.
I just want to like, people have this idea that if you put it in a computer, what comes out is like the word of God.
Correct.
It's like 100% correct. And that's entirely false.
Yeah.
Okay. If you put something in a computer and an answer comes out, you have to be incredibly skeptical, right? Because you have to understand that that computer is just solving equations, and that it doesn't tell you what to put in the equations. Okay, and if there's something that there's some like key piece of physics or key piece of the like model that hasn't been put in, you're gonna get blindsided.
Yeah.
Like I'll give like a silly example. Like you like trading, right?
Mm-hmm.
You remember I'm trying to remember who made this bet. I think it was it Paul Erdos and Julian Simons actually.
Okay.
They made a bet, I think, in the 1980s about commodities prices.
Okay.
And so the Erdos side was saying, okay, the number of resources is finite, and therefore, as people use more and more resources, the price of these resources will go up.
Yes.
Simon said, no, we always get better and better at extracting resources. The price is actually going to go down. So they said, pick 10 commodities, and in 10 years, we're going to compare the prices.
I do remember this. This is in Jen Simon's book. Yeah.
Yeah. And so if they went up, he would lose the bet. Mm-hmm. And they all went down.
Yeah.
And, people have said like, oh, it was just a fluctuation. It was just because the prices were low in the 90s or whatever, making excuses, basically saying that, oh no, this computer model that they used was actually correct.
Yeah.
But it wasn't, right? Because the computer model just didn't take into account that we're like humans and we come up with better ways of extracting resources. And that it's not just that, oh, there's more people, hence there's less resources. It's not that simple. And I think that's just a good example of, if you put garbage in, you get garbage out.
Yeah. That's pretty incredible.
That's why I'm incredibly skeptical of this AI stuff.
Yeah.
Right. So, you say oh, we'll just feed data to AI and AI will predict something. I'm not super confident in that.
I think what AI can do is learn what we're trying to teach it faster. So instead of you and I coding, we just say, hey AI, build this website for me, and I want it to do this and this and this, and the AI will understand my language and I'll be able to say it. I think that's the difference. The other thing that I think AI will do is that once we get to the point where it can somewhat simulate Ray Kurzweil, the singularity is near. You read that?
Sure.
Okay.
Sure. Keep on going.
He talks about this, with the singularity, and not like a singularity with a black hole, but the singularity for artificial intelligence is once we get to a brain that is equal to a human brain, whenever that is theoretically, and it will happen. Let's just say it's 2045. At the point that happens, the next day, it's not a little bit smarter than the human brain. The next day, it's 10 times smarter than the human brain. The day after that, it's 100,000 times smarter than the human brain. Because not only does it have all the capabilities that you and I have for pattern recognition that even the best computer in the world can't have. Not only does it already have that, it has the ability to rewrite its own code at the speed of light, or some astronomically fast speed. That's essentially what happens. And so now its ability to grow its own power and to completely not forecast all of human behavior, but just to think about, let's just say you had an AI and it was called Thor. And Thor was its prime directive was to create the highest number of happiness for the most human beings possible. So what would Thor do? The first thing Thor would do would be well, we're going to create these sex robots so that people stop having so many babies, so that people will start having sex with the sex robots, and then they'll there's all these theories about stuff that'll happen, or we'll create eugenics or stuff like that, so that there's no more disease, and all these horrifically immoral things that this artificial intelligence will come up with, because it doesn't have any morality, but it's just coming up with these ideas because of what, like you said, garbage in, garbage out. But that kind of thing, once we get to that point, the singularity where it's as smart as us, there's no, regardless of what we think about it or how fucked up it is, it becomes Skynet no matter what, because we can never turn it off.
But let me play devil's advocate here.
Okay.
So we were talking about how many aliens are in the galaxy.
Yes.
Okay. If you're right, all the aliens in the galaxy are robots. If that's not the case,
the aliens that get here are robots.
Robots can live forever, right?
Okay,
what would prevent them?
The aliens that come to Earth, I would agree with you, would have to be robots. But the aliens that still live on their home planet might still be flesh and blood or carbon based.
If for some reason life is actually a better mechanism for colonization, for lack of a better word, then all the aliens are going to be flesh and blood. Maybe there's something fundamental about the best way to promulgate is DNA. Maybe DNA is better than silicon.
Maybe DNA was the product of some artificial intelligence from a galaxy long ago, a time long ago, from a galaxy far, far away.
But like, I think time will tell.
Yeah.
But I'm very, I understand like DNA has like a lot of limitations.
Yeah.
Like dying kind of sucks.
Yeah.
You think that, oh, maybe if we were just on a chip, maybe we wouldn't die or something. But yeah, I think there's some like subtleties about DNA, and that using that like evolution as a way of like spreading life, it has advantages that maybe like a robotic type life would not have.
Interesting. Okay. Yeah. So I see what you're saying about the whole situation with AI. Anyway, the point I was trying to make before, when we were talking about physics and finance, one of the reasons why I like studying stock options is because it's a derivative of it's a derivative of an underlying. So in order for me to learn stock options, I have to learn stocks. In order for me to learn stock options, I have to learn bonds. In order for me to learn stock options, I have to learn ETFs and ETNs. In order for me to learn stock options, I have to learn futures, right? I have to learn about arbitrage. I have to learn about all kinds of things, about dividends. In order for you to learn about that, you have to learn about all these different things. In your case, theoretical physics, you have sat here, you're a theoretical physicist, and you have talked about astronomy. Probably more than half the discussions we've had either have to do with quantum mechanics or astrophysics. And if you look in the Wikipedia description for Albert Einstein, it says he is an astronomer. That is one of the descriptions. He is a professional astronomer. One of the things I noticed is that when you study astrophysics, or in your case, theoretical physics, you have to know all these other derivative underlying things. Like you have some knowledge of geology. Am I correct?
Personally, my geology knowledge is pretty weak.
Yeah, but you do understand chemistry.
People who study exoplanets,
yes,
know a hell of a lot of geology.
Yeah.
So like, you'll have astronomers, right, that literally go to like remote parts of the globe, to collect rock samples to try and understand, like, okay, when did this rock come out from the core of the Earth?
Yeah.
To try and understand how like the Earth like tectonics works, and then try to apply that to other planets.
But as a theoretical physicist,
but yeah, it's definitely like a very kind of like broad topic. You need to know a lot of things.
That's what I'm saying is like if you just trade stocks, you just got to know stocks. You don't have to know anything else.
No, it's the exact same thing. Like obviously so like these people who study like these protoplanetary disks, like how do planets form?
Yeah.
They need to know a hell of a lot of chemistry,
a hell of a lot of thermodynamics,
a
hell of a lot of astrodynamics, a hell of a lot of geology.
But the thing is,
chemistry.
Right, I think that's why astronomy is such an exciting field. Like
Agreed.
all the major discoveries that happen in science start in astronomy.
Agreed.
Because it's the most high energy particles, all the fastest speeds. We see them in space.
You have a laboratory. You have a vacuum that exists up there that you can that exists out there where I can actually watch. Again, if we had something orbiting within an atmosphere, now all of a sudden we can't predict the eclipses anymore, but the moon orbits in almost near vacuum. And now because of it, we know where it's going to be, and we know that it's tidally locked. We have all these experiments that are basically the solar system's running for us when it comes to gravity and chemistry.
Well, look how they discovered that the speed of light was constant. Do you remember?
Hold on. Well, oh gosh.
Is by looking at the moons of Jupiter.
Okay, yes, that is correct. So they use it.
Someone like would have to check this, but it's like I want to say it was like in the 1500s, like super,
that is correct.
Like super.
Oh my God,
ago.
I totally forgot about this. Yeah, this is in one of Neil deGrasse Tyson's books, which I'm sure you haven't read.
No, I haven't. It's incredible. It's basically like hundreds of years.
Well, it wouldn't have been in the 1500s. It would have been because 1601 is when they just first saw the moons of Jupiter.
Yeah. So sorry.
Yeah.
Some like. You were talking hundreds of years ago, right? They came to this realization, and likewise would say like magnetic fields, right? The strongest magnetic field you can make in the lab is like a few like Tesla, okay, versus like what do you have like around, the field of a neutron star? You're talking like millions of Tesla.
That's crazy.
And so it's like a different regime. If we want to study new phases of matter, we're better off studying neutron stars than trying to do stuff in the lab.
Right.
I'm not saying the stuff in the lab isn't important, right? Because it actually lets us calibrate what we see in space. But it's just like an entirely regime of like big, fast, high energy.
Yeah, that's absolutely incredible. So actually, I was going to ask you about this before and I forgot. A neutron star, so like a dead star. We burned off all the electrons. We don't have any more hydrogen in this star. The star now collapses in on itself. And instead of like normal matter like you and I are, where we are made of atoms that build molecules, these atoms have electrons and nuclei. These neutrons have burned off all the electrons. They are just neutrons that are sitting there compacted on each other. And what was it? The one shovelful equals the mass of the Earth or some shit like that. Can you describe what these are? And then they are spinning at just like an unbelievable rate.
So first, let's talk about the basic physics of a star.
Yeah.
Right. So like, why does a star hold together? So you have this big mass, right, where gravity is pushing all the gas in, and then you need some kind of force that's going to push the
Nuclear
gas
fusion.
out. So that so the nuclear fusion basically creates a bunch of radiation pressure, and so you can actually sustain or counteract the gravitational force coming in. At one point, you run out of nuclear fuel.
This is the point. Well, are we talking about? So there's two things here. Like, so our sun is going to run out of nuclear fuel, but it's never going to create iron. At the point that you get to 55 on the periodic table, the creation of new atoms goes from an exothermic reaction to an endothermic reaction, and once you get to iron, then everything collapses in. Is this something different you're talking about?
So think about it like this. So if you have a small atom, so like hydrogen, if you combine hydrogen atoms, so combine small
Get helium
atoms together, you release energy.
Yeah.
Okay. When you have a big atom, the way to release energy is to break it apart.
Okay.
Okay. And the cutoff is iron. So if you're heavier than iron, so more proton than iron, breaking it apart releases energy.
Yeah.
So what's happening in a star is you start with mostly hydrogen, and then that fuses together. And so every time you fuse, you release energy. And at one point, it depends on like the microphysics of the star. Okay, but the broad brush strokes is at one point, even if you're fusing iron atoms together, then you're not releasing energy anymore.
Yes.
And so then you run out of energy,
And
then
that's just gravity.
then you can't counteract the gravity. So you just have gravity pushing in. And so again, we were talking about, when does a physics theory break down? So our theory just broke down in a sense because we have nothing to counteract gravity. But there's going to be a new pressure that comes to save you. What new pressure comes to save you?
The nova, the collapse of all the gas on top of itself.
So first you have electron degeneracy pressure. So in quantum mechanics, you can't have two particles in the same state.
Yeah.
And so basically, if you have two particles that are in the same state and you try and combine them together, there's going to be a pressure that repels them. That's called the electron degeneracy pressure. Maybe that can counteract gravity. If that is strong enough to counteract gravity, you're going to form a white dwarf.
Okay.
Which is basically like a burned out star, and the electron degeneracy pressure.
But it's still hot.
It's still hot. Okay, it still has to like cool off. But the electron degeneracy pressure saves you. If it's not strong enough to save you, then it's going to keep on collapsing until then you have like neutrons that have a pressure as well. And you're basically trying to collapse two neutrons onto each other. There's some repulsion from basically quantum mechanics.
Yeah.
And maybe that's enough to prevent the star from collapsing. If that happens, then you have a neutron star.
Okay.
If even the neutron degeneracy pressure isn't great enough, then you're going to form a black hole.
Okay, got it. And then if you don't get to iron, you end up like what happens with Sol, our sun, where it turns into a red giant and then just burns itself out. Because Sol is not big enough to make it to iron. I think Sol makes it to like oxygen, or not even oxygen. I can't remember what it makes it, but it's not very big.
Yeah, there's different like fates for a star. Yeah. So I guess what I was describing was kind of like the extreme case.
Yeah, those are the big ones that end up collapsing, that burning out. But when Sol, our sun is called Sol. When
so you have an intimate relationship with our sun.
Yeah, son, my homie Sol. When Sol burns out, it is not going to collapse. There will be no supernova. When Sol burns out, eventually what happens is, I believe the outside of Sol eventually envelops the orbit of Mercury and Venus, and then it does not quite get to Earth.
It might get to us too. I don't know.
Maybe it could get to us, but that's 3 billion years from now, or 2.7 billion. Some.
It's okay. We will have moved to Alpha Centauri.
We will not move anywhere. We will be long since dead from nuclear war, starvation, GMOs, and all kinds of people who believe the Earth is flat. We're going to be long since dead before that. I do not personally. I'm not as optimistic as you. I do not think human beings make it another million years.
Do you think we're going to make it to Mars in our lifetime?
I think someone will make it to Mars and they will die. Absolutely. I am one again. Like I really do think. Have you watched the Nat? Of course. What am I asking you this for? There's a Nat Geo special called Mars.
I watched one episode.
It was fantastic. I loved it.
Actually, you should have Robert Zubrin on.
Should I? Well, get him on here.
Do you know Robert Zubrin?
I do not know.
He's the president of the Mars Society.
Yeah.
And he's the guy who had the brilliant idea of the key to space exploration, particularly Mars, is to use Martian resources.
Yes.
To be able to basically live off the land. And he's the one who innovated that idea.
Yeah, so you understand what they were going to do is like they put these tanks there. So like before I land on Mars, there's a tank there, and it's slowly going to pull this minuscule amount of hydrogen and oxygen out of the air and put them into tanks. It's going to take 3, 4, 5 years in order to do that. And once it fills it up, that's going to be my escape velocity, which is going to get me to my ship that's orbiting Mars and take me back to the Earth. That's essentially what the idea is in order to go to Mars. What I think gets downplayed, especially by Elon Musk, is how fucking hard it would be to live there. Like, for instance, the whole thing when you watch The Martian by Andy Weir.
I actually saw that one.
Thank God. All right. And the Martian by Andy Weir, they're living above ground and they're walking around out and outside, which of course you can't do that because there's no magnetosphere and there is no ozone layer. Like you're going to get irradiated from the sun.
I think the risk from radiation's overstated.
You think so?
Yeah, because like the way they calculate, how dangerous the radiation is would be the equivalent of like for alcohol saying like I know you don't drink.
Yeah.
Okay, but it's like if you drink like 10 bottles of wine, you're gonna die.
Yeah.
Right. But in a year. Right.
But you're there for 3 years.
But if you spread it out over a year, you're not gonna die.
Okay.
Right. So you have a glass of wine a day.
You think it's not that bad because in the Nat Geo special, and I've heard several other people say you're gonna have to live underground.
Like, I mean, it's probably a good idea to live underground, right?
Okay.
But we have astronauts who've gone to space for like over a year.
Yes.
None of them have cancer, right?
Right, but they're okay. There's a couple things. Number one, they're in a rotating plane. Number two, they're shielded by metal constantly the whole time. Well, I'm with you, but like they are still inside the magnetosphere when they're in the ISS. Isn't that correct?
Yeah, because they're in low Earth orbit.
Yeah, so they're not quite in deep space. And the other thing is, what was the other thing? I was thinking about the whole thing. You heard the thing where they put feces out on the outside panels of the spaceship to see if it
that only protects you from the solar flares, not the cosmic rays.
Yes, cosmic rays
poop does not protect you from
That's
cosmic
correct.
rays.
Yeah, they actually were trying the idea of using fecal matter in order to insulate from radiation, and it did not quite work. But so that whole thing happens. There's the problem of if there is no magnetosphere now, the idea of melting the polar ice caps with nuclear bombs like what Elon Musk wants to do, I don't necessarily think that creates an atmosphere. I don't know how the math works on that.
But you see, you're describing problems that are like you're basically saying like, oh, hey, Columbus, like how are you gonna like go from like East Coast to West Coast?
No, I agree, but that's not as far. And a lot of fucking people died on that trip, right?
No, I know, but like humans are badass. We've done some crazy things in history.
We're agreeing. Will there be people that will go and step foot on Mars? 100%. Will any of that first group get back? Fuck no. I do not think that first group that's going. The only thing they have in common is they are all going to die there. I do not think they're making it back. That's the only thing I'm saying. I think the infrastructure and the number of things that can go wrong in that 6-month period, the idea that they're going to be in something maybe the size of an SUV for 6 months, pissing and shitting on each other, I just find it very difficult to believe that those people are going to land there with enough psychological, like the muscle and bone atrophy. Granted, it's only 38% Earth's gravity, but there's just so many things that can go wrong. If you're a healthy, strong individual, the idea that we're going to be able to go there, maybe in a century, but in the next couple of years, the people that are going to go there and live, I do like the idea of what he's talking about, sending robots there ahead of time to create to create create farms and all this kind of stuff. You know what they're going to be eating though, right? The protein source? Rats.
I haven't heard that.
Tell me I'm wrong. What mammal, what creature can create the most amount of meat in the shortest amount of time and replicate on a trip to Mars? It's going to be rodents. They're going to be fucking eating rodents on the way up there.
No, so this is actually the best idea, I think.
Okay.
Have you heard of aquaponics?
No, I have not.
Okay, so so have you heard of hydroponics?
Of course.
Okay, so hydroponics is you put like nutrients and you grow the plants in water. So basically the roots are touching the nutrient-filled water. In aquaponics, you have fish pooping in the water.
Yes.
You filter out the poop, but the nutrients get converted with bacteria.
Yeah.
Okay, and that feeds the plants. Okay, and then you can take it like a step further. right? Because what are you going to feed the fish? Well, you feed them like crickets or mealworms.
Yes.
That you can feed the plants to.
Well, but that's the thing.
And so you can have a self-enclosed system. You're going to be eating tilapia on Mars. You're not going to be eating...
You're coming with the same conclusion I am. It's going to be things like worms, crickets, and rats. That's
No, tilapia. I'm eating tilapia. I'm not eating the mealworms are for the fish.
No, bro, you're going to eat MREs for about a week, and then you're going to die of dysentery. That's what's going to happen. I very much encourage those first people who want to go to Mars. Congratulations. You made it. You are proud explorers, and your names will be in history forever. They will name elementary schools after you, and you are going to fucking die up there. I do not think there's any chance that first group comes back. I'm going to go on record right now. I know it sounds negative, but I just don't think there's any way they get back.
Remember Newton? Mm-hmm. Like he wrote down calculus and discovered all this complicated physics that describes skyscrapers
going 0 miles per hour in Cambridge, England.
No, because he didn't ask himself like, okay, what's the limitations? He just said, let's fucking do it.
But he didn't even know there were. He was the one calculating the limitations. Like that was it. You know what I'm saying? And he did come up with a limitation. He didn't figure out what gravity was. Like there were certain limitations for him, like women, for instance. Like seriously, like I understand what you're saying. I'm not saying they're not going to go, and I'm not saying they won't make it there. But it's like Elon Musk says, I would love to die on Mars, just not on impact. And that's what I think there's going to be a problem. Now you do have some advantages, right? You don't have an atmosphere to like burn through on the way up or the way down. That's an advantage. You have less gravity to worry about. That's an advantage. And you do have certain minerals there. That's an advantage. You do have a carbon dioxide atmosphere that's like 1% the mass, the density of the Earth's atmosphere. That's an advantage, kind of, sort of. And you are far enough away from the sun that you're not going to get that much radiation. That's an advantage. And I don't know if you know this, but like there are points during the summer at the equator where it gets almost to habitable degrees of temperature on the surface of Mars. So that's an advantage for sure. But you're not going to find running water. There's never going to be a barometric pressure. You don't have a magnetosphere. You have massive amounts of radiation, and then help is 6 fucking months away. Those are the problems that you're going to have. Now, what do you think about Buzz Aldrin's idea of building a base first on Phobos or Deimos, and then from there going into Mars?
Now let's just do straight to Mars.
Just go straight to Mars.
First moon, then Mars. Yeah.
I love the idea of colonizing the moon in our lifetime. I love the idea of you and me being able to go to the moon in our lifetime.
We should put a whole bunch of telescopes on it. That would be the first thing.
Agreed, completely. There's tons of reasons for us to go to the moon. The level of experimentation that you could do, 100%. I'm way more interested in that than going to Mars. I would love, because that's something I think you and I can do, because it's 3 days there and 3 days back. That is something that we could do. The idea of going to Mars, I don't think you and me are going to Mars. I don't think that's going to happen. But the idea of colonizing it, I think the third time they try it might work. The third time everyone dies, they might get it right the third time. I think that's what's going to happen.
It's got to work first time. Otherwise, people are going to get... it's going to make really bad press.
It's going to make really bad press. Then 100 years later, they're going to try it again. Oh. That's what I think is going to happen. Speaking of Mars, why did you choose theoretical physics as opposed to astrophysics or anything else?
So... It sounds like a made-up story that you write for like a grad school essay.
Yeah.
But I actually read The Elegant Universe by Brian Greene.
Yes. That is, who told me to read that?
Might have been me.
Yeah, maybe.
No, so I read this, and yeah, he was just really good at explaining like quantum mechanics and relativity, and so he studied string theory. And so I was like, man, this is so cool.
So string theory is what brought you into theoretical physics.
So I wanted to understand like cosmology and like the Big Bang. And to understand that, like the best, candidate theory is string theory. And so that's kind of what like sucked me in.
So you do believe in string theory?
I mean, it's not like flat earthers, it's not like belief or not belief.
No, I understand what you're saying, but like the theoretical model of string theory was also one of the possible explanations of why you said before you'd have one electron with a up charge, one electron with a down charge, or at least that's how Michio Kaku explains it. That could be a possible reason why they are entangled. So do you think string theory would be an example of why that is? 9 dimensions, 22 dimensions, all this other kind of stuff. We're vibrating at a certain frequency.
So, okay. What I think is compelling about string theory is it tries to attack these kind of like serious questions, like how many dimensions are there, right? Without like having that as an assumption, right? Like all these other theories we talked about, like we assume, okay, there's 3 space dimensions and time dimension,
because that's what we have. Right. We have a 3-dimensional brain.
In string theory, you don't actually make that assumption. You just assume, okay, this is how I'm going to describe particles. And it kind of just falls out that, okay, the only way that I can have the speed of light be constant, right, is I need, depending on what kind of string theory you have, 26 dimensions or 10 or 11. And that's incredibly compelling to me because it's actually attacking those like fundamental questions. My biggest beef, right, with how we do science is it's very incremental, right? Like incremental is great for getting like PhDs that go work for like Goldman.
Yeah.
Right. You know, like, oh, I did this thing like 3 years ago. You're going to do like the same thing plus X. And if you do like a couple of papers, we're going to give you a PhD and then you can go off on your merry way.
Right.
That's not the way we like discover these like wild things. Right. The way we discover wild things is by like being like really bold and trying to, you know, really push the envelope. And like things like, why do we live in 3 dimensions? Right. Why is the mass of the electron what it is?
Yeah.
Like those are like really fundamental questions that I think we want to understand.
Yeah.
And, you know, just writing like the next model of inflation is not gonna solve that.
Got it. Oh, that makes sense. Okay. Got it. That's interesting because like during this conversation, like I studied astronomy. I have no experience with theoretical physics hardly other than the stuff that I read. And your knowledge of astronomy is obviously very vast, right? Almost everything we talked about, especially dealing with black holes, is definitely, you know, that's astronomical stuff. And so just how the two things seem like physics and astrophysics seem to go hand in hand with each other.
Yeah. So I would say if you come from a physics background, jumping into the astronomy is not super hard.
Yeah.
So like astronomers do incredibly like hard kinds of measurements, and understanding how their telescopes work is some work.
Yeah.
But if you understand the basic physics, then you can kind of like jump into it. Kind of going the other way is harder.
Yeah, I tried it. It's fucking hard. You're right. I was a astronomy minor, and I tried to get into regular physics, and it was definitely a little bit more difficult.
It's okay. The career prospects are limited.
Yeah, for both. I'm seeing that. All right. So now, this is the other thing I want to ask you about. So let's take. We're going to go right to the edge of physics into biology. Okay. How does non-living matter turn into matter? Is this something that you've discussed or studied or anything like that? We have organic chemicals. You said that you believe that we're going to discover life on Mars. How does this transition happen?
You know what? I have no idea.
No idea.
So this is my like pet theory. Maybe life's the best way to increase entropy.
Okay.
So the second law of thermodynamics.
Yes, is entropy. Yeah. Wait, what?
Yeah.
Okay.
So like the second law of thermodynamics is the entropy is always increasing.
Yeah.
Maybe life's a really good way to increase entropy. And so like
why is there a necessity to increase entropy?
That's a fundamental basically consequence of thermodynamics.
Yeah. No, I understand, but like we don't need to help entropy. Entropy is just fine on its own without life, right?
Right, but if we have life, maybe it increases even faster. Because like, what is life, right? So life, so say a cell, right? So a cell is this like enclosed system that you put energy in, and then it preserves homeostasis.
Okay.
Right. But in preserving homeostasis, the entropy has to increase, right? The same way that like say a refrigerator, right?
Yeah.
The way the refrigerator stays at 4 degrees C is you have to put energy in, and the energy gets pumped out after, and you increase the entropy, right? That's why you can't just like cool your house by keeping the fridge door open.
Yeah.
Right. So in a sense, a cell is like a great way to increase entropy because we've created this like little zone where we have homeostasis, but everything outside, all the space outside, you're going to pump entropy into it. And so maybe that's a great way of like increasing the entropy of the universe.
That's great. I have definitely an original idea. I have never heard that before. That would be interesting. So DNA, like we think of it as life, but what it really is just DNA. Natural selection just happened to create us hairless monkeys, and DNA is something that's pervasive all over the galaxy. Is that what you think?
I think that's why like looking for life on Mars is such a compelling question, right? Because if we do find life, right, the basic question is, well, does that life look like us?
Oh, I see, yeah.
Or is it completely different? Because if it's completely different, so say like, DNA is kind of like a file storage system, right? Maybe like we run Apple and like Martian life runs Microsoft.
DNA, but it's not related to ours.
Right, yeah. And that would be really interesting because then we'd have like a second example of life to study.
What if we go to Europa and find a third?
Yeah, that would be totally wild.
Yeah.
That would be totally wild. But see, then if it's exactly the same kind of life, then it brings about this question of panspermia. Did we come from Martian life? Did Martian life come from us?
So let me review this again for the girl who just got off work at the Rhino. The idea of panspermia.
No one got off work at the Rhino at 6.
6 a.m.?
They're all going for work right now.
They're going, no, I mean when they watch this. So the idea of panspermia is this. So tardigrade. They found near volcanic vents down in the bottom of the ocean, and they found these little. They're called water bears. They look like water bears when you look at them under a microscope. They found them frozen in Antarctica, and they found them frozen in the Arctic, and they thawed them out, and they've been frozen for thousands of years, hundreds of years, or thousands of years. And when they thawed them out, they fucking lived. They reanimated. These things, apparently, with extreme hot and extreme cold, these things would reanimate themselves, and they would live because they were so small. They could just deal with these. They're called extremophiles. These extreme changes in temperature. And somebody, and it wasn't the U.S., I think it was India or China, had this incredible idea of putting tardigrades out in hard vacuum. And they lived. And the consequence of that, when you understand how natural selection works, natural selection generally gives you traits that help you survive. The idea that there is some microscopic entity on planet Earth that can survive in hard vacuum, that can't get to hard vacuum. It's not like tardigrades have their own space system. The idea then would come, what if these tardigrades or some evolutionary descendant of these tardigrades was on a meteor or something collided with the planet Mars, and the planet Mars, the ejecta, spewed out some sort of meteors, and those meteors had these microscopic objects on there. Those microscopic objects then crash into a proto-Earth, right, with very little environment on it, very little atmosphere, and then those things are the origin of all life on planet Earth. That idea is called panspermia. So basically, DNA did not come from organic chemicals on the planet Earth and just magically turn into life. It actually came from somewhere else. And now the question becomes, where did that come from on Mars? Did that come from somewhere else? Is DNA actually just something that existed all over the galaxy, and it's just slowly being spread by meteors all over the place? And there's this one form of life, these little water bears, whatever they are, that they're able to just as long as we can get DNA on the surface of the planet, then we can then evolve into, different types of things. I don't know if that makes sense, because the thing about tardigrades is they're not single cell organisms. They're multi-cell organisms. And so I don't know, you wouldn't evolve back to a single cell organism. So you would have to start the evolutionary chain at where tardigrades are and move up. So I don't know. It's an interesting idea. But the idea that their life could survive a meteoric collision with the planet Earth without being evaporated, without being vaporized, is an interesting idea, and that's where the idea of panspermia comes from. Does that sound accurate?
That sounds accurate.
Yeah.
But I mean, so with mass transfer between Mars and Earth, I think the estimate is that there's 100 kg a year
that transfers between the two.
Yeah. And so,
and we're talking about an Earth that doesn't have the atmosphere it has now, so it could get to the surface.
And so you can basically study the meteorites that land on Earth and figure out, okay, how hot did they get on re-entry, right? And the temperatures that they experience kind of on the inside is much less than would kill bacteria.
Yeah.
And so in a sense, just normal bacteria could have made it.
Yeah.
But what you're giving an example of with extremophiles, that could be crazy, because it could go across, presumably the galaxy.
Yeah, we may be the remnants of some civilization that lived billions of years ago that had the same DNA that we did.
It brings up the question though of what's a more likely occurrence? So say you want to populate the galaxy. Mm-hmm. What's easier, to just have life form randomly, or to actually spread life with these extremophiles that you blast off into different systems?
It's still got to come from somewhere. At some point, you take the lithium and the nitrogen and the oxygen and the carbon, and you mix it together.
And so that's what I'm saying. What if panspermia is the main mechanism? It means that for life to actually start, right, you would need some kind of very specific conditions. Because in that case, it means I need life to start here, most likely by panspermia, not by, call them, natural processes. And that seems highly unlikely, because from these experiments that they've done, it seems that you could probably form life just from the conditions that you have in an early Earth.
So you've seen that, because I've got the opposite impression that they have not been able to form life.
Yeah, so they're not like forming life, but this is these experiments they did in like, I want to say like the 50s or 60s. They basically like, you take some like some jar, basically put in a bunch of like carbon and hydrogen and oxygen, and then you just pass a bunch of electrical current through it, and it starts to form these different kinds of like chemical elements that you need to form kind of like proteins and stuff. And so they haven't, like, I'm not saying they formed life, but they formed kind of like, it suggests that you're getting there.
Something random happened that we don't even know about.
And so basically what I'm saying is that it would be weird if there's only like one planet in the galaxy where life was able to form, and then it spread from there, because that means that there'd be something incredibly special about that place where life formed.
Yeah.
As opposed to just thinking, well, actually life forms pretty ubiquitously across the universe.
Could be. This is a pretty special planet. This is the largest Terran object in the solar system. And when you consider our environment compared to every other place, like the only place where there's like liquid anything would be Europa and Titan.
But we're just looking at one system.
Yeah, well, I mean, we're looking at one system, but there's thousands of bodies in the system. And
but I mean, the way to think of it, right, is like, so we have one star, and you were talking about the Goldilocks zone. Like, yeah, you could only fit like about one planet in the Goldilocks zone, but every planet has a Goldilocks zone.
Right. No, agreed. I'm not saying. I'm just saying this place is pretty special. The difference between the Earth and all the other planets is like there are planets that are somewhat similar to one another, right? Twin planets or whatever, and you get objects that are this that get to hydrostatic equilibrium, and some objects that don't, and it's just. When you look at the Earth and you compare it to everything else in the solar system, it could not possibly be more different. I mean, it's very tectonic plates, running water, an atmosphere of mostly nitrogen, the ability to like see through it.
There's like 400 billion stars.
I understand. No, I'm not saying that there probably isn't something else. Now, the likelihood that it gets to the point where natural selection causes the civilization there to have podcasts with physicists, I don't know if we get to that point, but who knows? I mean, I'm not sure. Maybe everything that we could possibly imagine exists somewhere. There's a whole, civilization full of elephants. I don't know.
That would be cool. I'd go visit that.
Yeah. But here's the other thing. Like, you have to think about it from an evolutionary standpoint. You and I are not having this conversation because there was a necessity for the universe to discover itself. You and I are having this conversation because our ancestors needed to hunt gazelles. You and I are having this conversation. The reason why we have kneecaps, the reason why we have hip flexors, the reason why we have the ability to hold our head straight while we're running, the reason why we have ball and socket joints in our shoulders and the ability to throw objects overhand is because we're hunters. We're long distance hunters. Evolution made us that way. We had to solve problems. Those problems then eventually led to Sudoku puzzles and nuclear bombs and then theoretical physics. But you and I are not having this discussion because evolution. There was no evolutionary pressure for you to become a theoretical physicist, right? There's evolutionary pressure for you to get a job, but like that's you know what I'm saying?
Actually, the reason I did theoretical physics was to not have a job.
Really?
I was sitting in my kitchen talking with my dad, and I was like, I don't know what major to do. Should I do engineering or theoretical physics? And the conclusion I came was, if I want a real job in 4 years, I'd do engineering. Yeah. If I didn't want a real job in 4 years, I'd be a theoretical physicist.
And look at this. You're going to be working for Goldman here pretty soon, making millions of dollars managing a hedge fund just like me. That's pretty awesome. Dude, I think we covered everything. Is there anything we missed?
You can have me back on with a flat earther.
Okay, dude, I definitely want you to flat earther. I think we just completely did an Astronomy 101 class here. I think we got the whole thing. We went into some pretty deep places. Talked about Isaac Newton, William Herschel, talked about Johannes Kepler, talked about Galileo. We talked about everything, man. Gravity. We talked about the strong and weak nuclear force. I think the only thing we missed was Schrodinger's cat.
Yeah, we'll save that for next time.
We'll save the Schrodinger's cat for next time. You should definitely look that up, guys. This is the longest podcast I've ever done, so thank God for that. We did it. I told you, Travis. I got a physicist on here. We did 3 hours. I told 100%. You this was going to happen. I told you. So now, here's the thing, guys. Like, share, and subscribe. We went we zigged as far as we could zag. Last week, obviously, we had two bikini models on. This week, I have a theoretical physicist, and next week, I have a 15-time playmate on the show. We are trying to go in many directions as we can. We had Dan Bilzerian on the show. I got Justin Ross Lee. Just told me he's coming on. What's her name? Jessa Rhodes told me she's coming on. We have 2 F-16 pilots and 2 F-18 pilots that are going to come on. We're going to talk about flying in the military. We're going as many different places as we can. I have to get around to scheduling Flat Earth Dave because I want him to come on at some point, and maybe I can zoom you in when we do Flat Earth Dave. But guys, I want to say thank you so much again. when I was hosting the Maxim party, the number of people that came up to me, they were like, "I love this podcast. It's really great." And I just am shocked. Like one of the things when people come up to me, random people that I've never even seen before, had no idea who they were, and they told me that this was something really interesting to them. If you liked listening to me talk about OnlyFans, I hope you guys can at least use that curiosity that you have to understand when we're talking about astrophysics, thermodynamics, the laws of motion, the movement of planets, and the history of astronomy. I hope that you guys can take that interest, that intellectual curiosity, the reason why I started this podcast in the first place, and listen to this whole podcast and understand that the world is bigger and brighter and more interesting than maybe you even imagined. Because one of the reasons why I don't believe in the zodiac, you know why? Is because regular physics is way more exciting to me than the zodiac. You know what I'm saying? The reason why I don't believe the Earth is flat is because the actual Earth we live on is fucking awesome, and there's so much great stuff that we can learn about it. So thank you so much, man. Thank you once again. You need to follow this guy. Let's make him famous. Thanks
for having me on the show.
Let's make him the Neil deGrasse, the Canadian Neil deGrasse Tyson. Let's make this guy famous here. We love you guys. Thank you so much for coming out, and we will see you next week.